Here we go. Okay. Now it should be recording locally, and then I'll upload it. I wonder how much space I actually have on the Zoom servers. Oh well. Okay, let's start with this exam. Give me a second. I gotta paste over these questions. Okay. All right. So question one deals with okay. Don't know why I didn't update there. Second. The heck? In the right folder. Yeah, I am. Oh, I know why it's not syncing. There we go. Sorry about that. Okay. So label the following species as aromatic, anti-aromatic, or non-aromatic, right? So this, we do the criteria, right? You gotta be careful about hybridization in lone pairs, right? Things will hybridize from anti to non if possible, right? That's the key. That's usually only if you have heteroatoms, right? So for the first one here, let's start with, I guess we'll call this A, right? We have a, do we fit criteria 1? Yes, right? So we have a closed ring, right? It's all planar, right? We have a pi bond in use with the nitrogen here. We have another pi bond, so all the carbons and the 3 carbons and the nitrogen are all within the plane. And really what comes down to is, will one of the lone pairs, if we put in an p orbital, right, will this make it aromatic or anti, right? So remember, there is a lone pair on this nitrogen here, right? Its p orbital is already being used, right? So that lone pair is going to be outside of the plane of the ring in an sp2 orbital, right? So don't worry about that lone pair. Remember, whenever there's heteroatoms that have a pi bond to them, their lone pair, I mean, their p orbital is already in use, right? So we have 2, 4 from the pi bonds. Let's write this down here. 4 electrons from pi bonds, right? So if we add 2, it's going to make it aromatic, right? So this is, as people said in the chat, it's going to be aromatic, right? If this was something like, I don't know, like that, right? And we had lone pairs here, right? What would you expect this molecule to be?
Non-aromatic.
Non-aromatic, right? Because as we look at it, yeah, it could fit criteria 1, right? But like I said, whenever you have heteroatoms, just check to see what happens if you put 1 lone pair and assume it's sp2, right? In this case, if we made oxygen sp2, put the lone pair in, we get 8 electrons. That is an anti-Huckel number, right? And that would make it anti, right? So instead of being anti, right, in this specific case, the oxygen will hybridize to sp3 and just make this entire thing non-aromatic, right? So next one here, right? We have, what is this? I think this is Perol. I think it's Perol, forget. So we have two so far. It fits, what's it called? Does it fit criteria 1?
It being cyclic, yes.
Right. What about nitrogen here?
SP, is it S? That's confused me. That's confusing me. SP3?
It is sp3. It has
Yes.
4 electron domains, right? So,
Nitrogen can have 4 bonds along with the positive charge.
so the positive charge, right? Originally, this compound would look like this, right? And it has 1, 2, 3, 4, and then there's missing an H, right? So this is how this would normally look. And this would be aromatic, right? Because then this would be in a p orbital. This would all fit out. This is sp2 hybridized. You have 6 electrons, right? But now, since it's the whole thing is the positive charge just means it has an extra proton, right? Because normally its formal charge is 0, but since you bonded it to another hydrogen, it gains a positive formal charge, right? So
Yeah.
because it has 4 bonds, right? At that point in the molecule, right, it's going to be sp3 hybridized, right? Which means it does not fit criteria 1, right? So you just gotta be careful. Anytime as soon as you run into an atom that does not fit criteria 1, right? It's going to, you can literally just automatically mark it as non-aromatic, right? Let me just read the chat here. It said plus is an empty on carbocations, right? So when I was saying that, I specifically said whenever you see a carbocation, think of it as an empty p orbital. When you see a carbon ion, right, it's a filled p orbital, right? On nitrogens, oxygens, and other heteroatoms, right? It just varies, right? But on carbons, that's generally how you could kind of think of them. So, oh, why is my brightness so low? Give me a second.
I have a quick question about the second compound we just went over.
Mhm.
So the thing that's confusing me right now is that, okay, we established that this is non-aromatic, but we done an example with like 2 oxygens, and we made one sp2 and one sp3.
Right.
So I'm like,
No. So I know what example you're saying, right? This one, right?
yeah, that one.
So when I was going over this example, right, I said we can't pick and choose to be sp3 and sp2 because if one is sp3, automatically it's non-aromatic, right? But if both were sp2, then it would be anti-aromatic, right? So you can't pick and choose because once you pick and choose, that means at one position, that ring is going to be sp3 and it's out of the plane and you don't fit criteria 1, right?
But the best way for this molecule to exist is for one to be sp3 and for the other to be sp2, right?
For this one?
Yes, for this molecule. For one oxygen to be sp3 and the other to be sp2. I'm
Okay,
not disregarding aromaticity rules and everything. The best form of existence for this molecule.
I mean, you can't really say. I mean, it would be hard for me to even say like, can you prove if one is sp3 or sp2, right? I mean, if it's sp2 has 1 point, sure, you'll have some delocalization going on that part of the ring, right? I guess you could say a negative charge. But in terms of how stable that makes it, I wouldn't really be able to comment on that. Besides, like doing actual experiments to see its energy levels.
But it makes it more stable than both of them just being sp3. Because I'm just basing this off of an example that the professor did in one of his exams.
Yeah,
He kept one sp2 and the other sp3.
Yeah, I know what he's talking about. It's actually one of the exams that the professor posted on Blackboard, and he said that one of them is going to be sp3 and the other one is going to be an sp2 to avoid
steric interactions or something like that.
The question was asking basically asking predict the hybridization of the oxygens in the following molecule given this molecule.
Okay, let me just quickly. Do you guys remember which exam it was online?
I can find that.
The 2019 one.
RS or PR?
I'm not sure, but it's 2019.
Okay.
It's I think it was on the same question was on both exams.
It's on RS.
Okay, let me just grab that real quick.
Sure.
Stick.
Real quick, you see the example you drew with the 8 electrons? The oxygen would only participate if it helps, not if it makes it anti-aromatic. The oxygen would not participate in the conjugation, right?
Right, because if it adds if it adds a non-Huckel number of electrons, right, it's going to make it very high energy, right?
Yeah.
So it's going to be sp3 and just be non. 2019 are S, right?
Question 5 or 6.
It's question 5.
Oh, explain access predict 6 pi electrons would likely be in conjugation. Yeah, I'm just looking over the answer. One oxygen would be sp2 hybridized and one would be to avoid an 8. So yeah, I guess his reasoning is the 6, whoever was talking before, right? That delocalization effect, and this would be negative, right? This delocalization effect is a stabilizing factor, right? So that's kind of what he was pointing out, that if they're both sp3, right, you won't have any conjugation happening, right? So that's kind of that's combining really conjugation with aromaticity, right? So yeah, I guess that makes sense, because conjugation, right, delocalizing things in more position will always stabilize something. So based off that logic, yeah, I would agree, right, that you have essentially 1, 2, 3, 4, 5 locations electrons can travel through, right, as opposed to 1, 2, and 1, 2, where they're kind of limited, right? I didn't even know he had a question. That's a really good question, actually. But yeah, then you wouldn't be using aromaticity. I mean, that question's a combination of really the chapter, 16 concepts of, conjugation and delocalization through multiple pi bonds, in addition to anti-aromaticity, right? Yeah, so hopefully that explains that.
Sure.
I guess, yeah.
So this molecule then is going to be non-aromatic, right?
It's still going to be non-aromatic, yeah.
Okay, thank you.
Regardless, but in terms of if you had to specify each hybridization, then you could do what he says in terms of increasing the amount of conjugation you have, right? Because that just means that the electrons can jump through p orbitals, right? And that's always good for a molecule. The more you could spread out electron density, the more low energy that molecule is. So that was his reasoning, and that makes sense. But in terms of the entire molecule, yeah, it will always be non-aromatic, because that one oxygen will never be sp2 hybridized.
Oh, I thought his reasoning was because the molecule was, you said things don't want to be anti, so that's why it's going to be sp3 to become non-aromatic.
Yeah, so that's what I was saying, is that this one will always be sp3, or whichever one, right? Is one will always be sp3, right? Because at that point it's non-planar, right? But then he asked specifically, why is, I guess, one sp3, one sp2, right? And then your reasoning for that would have to do with conjugation and delocalization, not aromaticity.
Okay,
Yeah.
thank you.
Okay, that's good. I mean, it's funny because the textbook had that question, right? That's a good question. That would definitely trick a lot of people there. So wait, which one is someone, Isabella? This one is always going to be non-aromatic. But once again, right, if you can delocalize stuff, right? So basically let me kind of highlight this, right? This portion of the molecule will all be planar, because it will allow electrons to move freely between 5 atoms, right? As opposed to 2 individual atoms, right? Okay, so here we have a protonated pyridine ring, right? The third one here, right? Same thing. Do we fit criteria 1?
Yes.
Aromatic.
Right. Just want to draw all the p orbitals, but just remember, every time you have that pi bond to something like nitrogen or oxygen, right? It's already in use. Same thing as the molecule before, right? This is just protonated. Normally pyridine looks like this, right? This kind of shows why it's a good base, right? Because that base is localized, so it would want to find and attach to a proton, right? But its hybridization here is still sp2, because it has 1, 2, 3 electron domains, right? And the other one we had 4, right? So this one is aromatic. Okay, this one's next one's a polyatomic,
Just a quick
poly-
question.
polycyclic.
Sorry, I have a
what's-
quick question.
Yeah, what's up?
Yeah, let's say that positive charge was a negative charge, right?
Mm-hmm.
So then that negative charge, would that participate as well? And it would be 8 electrons?
Well, if that positive charge was a negative charge, so let's look at it when it's neutral, right? Right. If we got, the only way we could get a negative charge would be to add like a London lone pair or anything, but that would make this break the octet rule, right? So the real answer to the question is it'll never have a negative charge, right?
I just realized I had a double bond. Oh,
Yeah.
never mind. Okay,
It's already kind of maxed out there, right? So it'll never have a negative charge.
gotcha.
Okay, so the polycyclic aromatic rings, right? PCH, polycyclic, I forgot. Polycyclic aromatic hydrocarbons, right? So we said there's 2 ways you guys can do this, right? You could look at one ring individually, or you could just do the full number counting, since that usually always works, right? So if we look at one ring individually, we have this plus, whoops, this, right? So individually, they're both aromatic, right? We could just put one lone pair, 2, 4, 6, all planar. This will be sp2, right? Same thing for the other one. Or you could do the entire ring, entire kind of molecule as one aromatic ring. So you have 2, 4, 6, right? If we hybridize both these oxygens as sp2, you get 8 and 10, 4n plus 2, that works for 2, right? So either way will work out. I think for the most part that counting it as one ring works, but breaking the ring method also works either. So whichever one you guys find easier. So this one is aromatic. And then the last one, right? This is where one of those examples, right? Where I said sometimes you'll have things locked into anti-aromaticity, right? So we have a planar ring, right? It's a ring and then everything here, the p orbitals, right? Participating in pi bonds. We have 4 electrons here. That fits 2n for n equals 1, right? So we're locked into anti-aromaticity. So this is one of those few examples, right? Where you're kind of stuck, right? There's no heteroatom that can, hybridize. None of these carbons will dehybridize or rehybridize, I should say. Which one? Sorry, I'm just keeping up with the chat right now. Someone is saying, how is the second one non? This one? All right, give me a second. But everyone's good on what this is anti, right? It's locked into anti-aromaticity. So like cyclobutadiene, I guess. Yeah, this is cyclobutadiene, right? That's one example. How about if I gave you guys this? Two, 4, 6, 8.
That's the exception, right?
That's the exception. 8-annuline. There's another name for it too. But 8-annuline and then 10-annuline, right? 8-annuline you expect to be anti-aromatic, but it's not because it's big enough to conform out of a plane. And then 10-annuline, right? It has 10 electrons, right? But there's steric repulsions between the hydrogens that are inside the ring. And because of that, it conforms out of the plane as well, right? And back to someone's question there. Hopefully, I think people in the chat seem to have answered it, right? But the main thing you're looking at here, right, is, remember I said always check for criteria 1. And then when you get heteroatoms, right, then you kind of play around to see whether fitting criteria 1 makes it stable or unstable. Someone has their mic on with the keyboard typing. You could shut that off, please. Thank you. So in this case, right, we look at one atom, right, and boom, right here, nitrogen has 4 distinct electron domains, which means by definition, it has to be sp3 hybridized, right? Same thing if I gave you cyclobutene, right? you see 2 carbons with the pi bond, but remember this carbon here, right, is sp3. Yeah, so 8-aniline is non-aromatic. Same thing, like if you see cyclobutene, right, just like I said, always check each atom in the ring, right? When it's heteroatoms, then you have to play around with it. Okay. Second question I liked a lot, actually. I don't know if you'll ask something like this again, but this is a really good question. Rank the reactivity in Diels-Alder reactions. This one's not as easy as the dienophile one. This one you got to think about because it's all alkyl groups, right? Where is let me paste it. Okay, let's scroll down, right? So rank the following dienes in order of decreasing reactivity. Yeah, all right. No, I don't mind. Take 2 minutes, 3 minutes. Try not to look at the answer key because you're not going to be able to do that Tuesday.
Sure. All these exams are just BISCO's exams, right? That you have.
The ones I have are more or less almost all BISCO's exam. Let me actually look in the folder.
All right, thank you.
Where's the old exams? So there are some that are not BISCO's. I believe those are the I want to say the 2019. I thought I had some 2021s. I don't think I put those because those were pandemic type exams, which means they were harder because they're open book. I don't remember if the other 2019s, they might, 1 or 2 of them might be Andia's, but he uses the same format and style. So like everything, there's only maybe 1 or 2 exams from like boson in there, but everything else is all BISCO. Same thing for organic. Well, actually organic 1, BISCO never teaches. So that's all Andia, but everyone here is taking organic 1. So I have a question about the one from the 2019 exam. Why can't they both be sp3? So we did that question once, right? And right, this one, while everyone is else working on the problem, right? When we did it on the textbook, right, we were just dealing more in terms of aromaticity, right? So that's why we labeled both of these kind of sp3, right? Because if we picked and choose, right, it would never be aromatic, right? If you pick and choose. And if you pick both of them, right, as sp2, then it'll be anti, right? But the question he asked on one of his exams was, you know, where was it? Predict the most likely hybridization state. And he kind of added on to what kind of, I guess, falling back to previous chapters, really just kind of, I guess, the logic really of organic chem is that the more you delocalize things, right? Because I always look at pi bonds and p orbitals as a tunnel system, right? So you have this tunnel that electrons can move through, right? So when that tunnel is limited to only 2 sections in the molecule, right? Essentially, you have a gathering of electron density here and here, right? And that would make this kind of high energy because that means electrons are localized at those carbons, right? But now if you added another position that allowed you to get through both of these tunnels, now you're basically making electrons flow as far as you can within the molecule, right? And if electrons are less accessible, right? So this is kind of the reasoning of why it would be low energy, right? Because things that are reactive, if they're electron rich, that means electrons are localized. When electrons are delocalized, the reason they're less reactive is because it's harder to reach them because they can be in any of these 5 spaces, right? So that's why what he was looking for was to see if you noticed that conjugation, right? And that also notice that if you tried making both, it would make it very unstable because it would be anti-aromatic. That's a good question. Well, I wouldn't say hopefully because I want y'all to do well, but I like questions like that on exams because it's like those actually test if you know everything. Okay, I think hopefully everyone's taken enough time to go over this, right? All right, so dienes, what makes them more, there's two ways to look at them. One is just straight up electron donating groups, right? The more electron rich your diene, right? The more willing, the better its HOMO is going to be, right? Because there's more electron density being pushed into it, right? Which increases its reactivity. So in this, kind of unfortunate thing for all y'all is that it's all alkyl groups here, right? And then you have to think about, really the sterics of the Diels-Alder reaction, right? And there's a kind of a reason why he drew, right, to kind of give you a hint, was he drew these all as S-trans, right? And this is a matter of what's the energy barrier, right? Because remember, going from S-cis, right? S-trans, right, which is low in energy because groups are further away from each other, to something like S-cis, right? It requires a certain barrier of energy, right? And S-cis is much higher in energy, right? So depending on how big this barrier is, right? Because in a reaction vessel, all these like dienes, right? They will exist as the trans, but that's why, Diels-Alder reactions are done at high temperatures, right? So there's enough energy for it to conform, get into the S-cis formation and proceed with the reaction. So really what this kind of question is looking for is which ones are most likely to conform, right? But right off the bat, you could already pick one, right? That's going to be the least reactive, right? And which one, if I label these A, B, C, and D, and E, which one can you say automatically is going to be the least reactive? So you have a couple of mixed answers. Any more
D,
takers? D.
In trans.
Right, so D, right, if you notice, right, it's a S-trans diene, right, but it's locked into S-trans, right, because the dienes are part of a ring, right? So there's a 6-membered ring and then the other alkene is sticking out of it, right? So the only way you could make this S-cis would be having to break a bond, right? And that requires way too much energy. So this is basically kind of conformationally locked into an S-trans position. So it will never be reactive towards a Diels-Alder reaction because it can never reach so S-trans and S-cis, once again, right, has to do with the relationship of the alkene groups, right? So when you have a conjugated alkene, right, generally for dienes, right, the S refers to, I guess, the sigma bond between them, right? And then when the groups are pointing away from each other, right, this way and this way, right, they are trans, like in an alkene, right? If you had like something like Cl, this is trans alkene. This is cis alkene, right? Don't think about the cis trans EZ for alkene. Those just for comparison, right? The specific terms you use for when you have conjugated stuff is S cis, S trans, right? So the same thing is now is if I rotated this group, right? This group would push in this way, right? And now these groups are on the same side, right? So they are cis to each other, and we call that S cis. So that's S cis and S trans. I'm pretty sure that S is for the sigma bond. But either way, that's just the, I guess, IUPAC or chem notations for that, right? It's talking about the relationship of the alkenes or olefins, whatever you want to call them, right? And it kind of uses the same basis of trans and cis that you've seen in alkenes, right? Or rings, right? Whether things are on the opposite sides, or which is trans, or whether things are on the same side, which is cis, right? So for Diels-Alder, you need S-cis, right? That's the whole way that cycloaddition works. And to reach the S-cis from S-trans requires a certain amount of energy. and it differs based off the type of dienes you have, right? So there's another one here that we could also label its position between A, B, C, and E that we could also kind of right off the bat.
E.
Why?
It's locked, cis.
Exactly,
Locked.
right? So in this case, right, we don't even have to put in any energy, right? So whenever you have cyclic dienes that are as cis, right? So like cyclopentadiene, so this is cyclohexadiene, right? You guys have seen this, right? You have seen this is furan, right? These are already locked in that S-cis because they're part of a ring, right? So when you see something locked in either S-trans or S-cis, right? If it's locked in S-cis and the other choices aren't, right? Then that one is going to be the most reactive. Then obviously if you had multiple, like let's say if I had another one that looked like this, right? And I don't know, I put like a OME group, let's call this F, right? E versus F, which one would be more reactive now?
F
And why is that?
has an electron donating group.
Exactly, right? So then you might notice certain differences like that. So the first priority is if it's locked into a certain kind of conformation, right? Then, you know, then you could kind of compare electron donating groups or whatever, right? And then, but if the thing is, if the electron donating groups are similar, like we kind of see in A through C, then we gotta figure out, you know, how likely it is to rotate. That's kind of what this question was going for, right? Is you gotta make sure you do the rotations right. So let's do those. So if we start with this, right? Like I said, as I think I did this when I was doing one of the review sessions, like a Friday or something. Somebody asked how to rotate it. I don't know if I did it in the recitation, right? Keep one part of the molecule the same, right? Rotate the other side, right? So only rotate this side. So now if I was to draw this, right, it would draw this, right? And it's kind of flipped image. So this would go like that, right? Is everyone clear on what I just did, or you guys want me to do it again, right? Keep one side same, right? Maybe I'll use like a different color, right? Then when we do the rotation, right, you could literally just draw it. The alkene part, you're literally mirroring it. If you think of this as the mirror plane, right? And boom. There you go. Right? So that's how it would look in the S-cis formation, right? So these are both inside. Let's look at the next one. That we're going to keep this side the same. We're going to do this, mirroring it like that. That's that one in S-cis. And then you have this. Same thing, keep this side the same. Draw your alkene. Oh, wait, did I miss something? Yeah. And there we go, right? So those are the three of them in S-cis form, right? So now, right, this is where I said that kind of barrier of energy thing comes into play, right? Is steric interactions is really what you're thinking about, right? That's why you have to remember. That's why the book mentions, and why your professor probably mentioned, why it takes energy from going from S-trans to S-cis, right? Because if we did a rotation here, like call these A, B, and C, which one will be the hardest to do the rotation on? So we have mixed answers, right? So some people say C, people say A, right? So the hardest one to be doing the rotation on, right, is going to be the one that has the most steric interactions, right? Here you have a methyl group and a methyl group both pointing inside towards each other, right? Those are, compared to hydrogens, relatively large, groups, right? If you compare it to just a pure hydrogen, right? So the steric repulsion is going to be greater between two methyls that are both inside as opposed to when they're outside, right? So when you're maximizing kind of inside groups, it's harder for that thing to conform, right? So A is going to be the hardest to rotate, which means if it's hard to get to as cis, right? Would that make it more reactive or less reactive? Less reactive. So what would you, based off what we have, we already labeled this as 5 least reactive. We already labeled this as 1 most reactive. Where can we put A right now?
4.
4, right? Because we know it's going to be harder to rotate than B and C because both those groups are inside, right? So
Can
we
you
could put,
explain why D is 5?
yeah, I'll do it afterwards. So now between B and C, right? Which one do you guys think now based off that logic we just literally discussed a few seconds ago? Which one do you guys think is going to be less reactive?
C is less reactive.
C, right? Because now you have 1 inside group and 1 outside group. Here you have 2 outside groups, right? So there's going to be minimal. Okay, so maybe I'll write it down too. Most steric interactions, least steric interactions, and then obviously this one is going to be kind of middle. I'll just write, but it just more has to do with that. It's a mixture, right? 1 inside, 1 outside. I guess it would be the hydrogen here that's repelling this. All right, so if B is going to be, I guess, the easiest to get to, it would be the most reactive. So we could put that as 2 and this is 3, right? So really, once you kind of, with all these ranking questions, right? Maybe even if you get an acidity or basicity question, right? You could, in addition to obviously using all the theory and logic you learned from the class, you could use the process of elimination too to see what's left, right? So once we determine 2, you kind of can play around to figure out which ones are left, right? And someone asked why D is the least reactive, right? Because this, no matter what you do, right? D, draw it out here. Oops. Right? No matter what you do, if you try to rotate this way, well, you can't rotate it that way. You can't rotate it this way. It's locked into a ring, right? So what you want, if you want this to be in a Diels-Alder reaction, right, we essentially need something that looks like this, right? Then we would have, I don't know, it would be a broken bond, like looking like this or something, right? Essentially, we broke a bond in order to get this. And that requires way too much energy to do, and it would probably really never happen. Right.
Sharuk? Sharuk?
Yeah, what's up?
Okay, so if we ever get a question like this, we always have to look at sterics, and then, as you said, if the groups are pointed inwards, they're least reactive, and if the more groups they have pointed outwards, they're more reactive than ones that are pointed inwards.
Okay, so let's write some check guidelines here, I guess, right? Since you might get a diene or dienophile questions. Check for S locked, right? So always check first if you have a locked S configuration, right? So if I compared something like, I don't know, this versus cyclopentadiene, right? Automatically, right? One is locked into S, right? Doesn't even matter if I put in like an electron donating group, right? The cyclopentadiene will always be more reactive, right? Because you don't need that much energy. The reality is, this is why a lot of people don't really like showing, as at least in the Clayton book, Clayton doesn't like showing the 1,3-butadiene because it's more of a molecule that exists on paper, right? And no one really does reactions with it because it's hard to work with, right? So S-cis is always prioritized if it's locked. Then I guess the next thing you can look for is, like once you determine based on that, is any sort of electron donating groups, right? So if you have a more electron donating group, so let's say if I compared something like, I don't know, this OME versus this, right? You have an electron donating group here, or even if I put this on the inside, right? It doesn't matter if it's on the inside too, right? This has more electron density in it, right? So electron donating groups, I guess would say take the next priority, right? Yeah, like I said, it all comes together. That's why I'm not putting this as a 1, 2, 3, 4 thing. It's just things you have to check for, right? So then the next thing is ability to conform to cis, which is what we kind of just did in this question for choices A through C. But it's like if you have things that are preventing it or making it harder, right? Something like this versus something like this, right? We have a, actually no, in this case, you guys tell me which one would take priority here. Even if I drew it like this, you can consider this out. The alkyl group, this one's a kind of a hard choice to say. Maybe I shouldn't draw it like that. We'll just compare basic stuff, right? I can't really say, if the sterics like overpower the things, but like, let's say you had an inside versus outside situation, right? So then you would look at steric interactions, right? So those are 3 things really to look for when you're ranking dienes. Check if the cis is locked, look for electron donating groups, and then see if you have an S-trans, like a linear or an open chain, I should say, an open chain diene, right? What's its ability to transform to S-cis, right? Just make sure you, yeah, what's your question?
It's about this. So if you're comparing two dienes, one of them is like the two groups are two alkene groups. The alkyl groups are pointing inwards, and then for the other one, they're both pointing outwards. But the one that has both of them pointing inwards has an electron donating group. Does that make it better regardless of the sterics?
It's a good question, and my answer to that is most likely I would highly doubt he would give you something like that on the exam, mostly because it's hard to qualitatively assess that, right? Remember, kind of what you're doing on all these exams is how much you could just use basic theory and knowledge to, assess things, right? But at a certain point, like that question, that's a great point. Like essentially what you're saying is if you had something like,
I think like if you look at the first structure and the third structure, that's kind of like the same thing, but one of them has an OME group. So like which one would be more reactive between the first and the third structure?
You mean these two?
No, the first one and the one.
The first and the third and this?
Yeah.
Oh, the OME for sure, right?
Okay.
Right, because that's an OME group versus an alkyl group, right? But what I'm sorry I didn't see your name there, but whoever was asking was something like OME versus something like that, right? Where it's like this would transform, but there's no steric interaction inside, right? Is that kind of what you're trying to get at?
No, I meant like remove one of the OMEs from the first one. And then for the second one, add like 2 alkyl groups, but both of them pointing outwards.
Oh,
yeah.
okay. So
and for the OME that you just removed, just add an alkyl group instead.
So if you had this,
yes,
right, and then we'd have this one. So this would be pointed. Essentially, it would look like that.
Yes.
Right, and then this one would be that. I guess that one you could say the other one because of OME, but like I said, he probably wouldn't get you something where you'd have to think that much. I would personally say it's the one with OME just because oh yeah, because it just has more electron density donation. But the issue where I guess what you're, it's a good thing that you're thinking about it is what about the steric repulsions? It's just, will that overcome the electron density that it adds? Right. And like I said, I don't know if he'll ask you something that difficult because it's hard to determine without actually experimentally doing it. Right. Because when you actually, prove the data, you could say, oh, this one's this. But like, maybe qualitatively, I say, oh, the one with more electron density. And then someone actually does the research and, you know, figures out it's the other one, right? And, you know, I don't think you'll take it that far, right? It's enough for you to like basically definitively say one over the other, right? Things like that is, you know, if you're interested in research, you could always do that, though. No one really researches Diels-Alders like that anymore. Really,
Sharuk, what if he threw in, I don't know if he would do this, but an electron withdrawing group, would that make a diene or a dienophile more reactive or less reactive?
So a diene is electron rich, right?
Yeah.
So if you add an electron withdrawing group, what does the electron withdrawing group do?
Well, it's taking electrons away from whatever else is.
And then what does that mean in terms of Diels-Alder, right? Your thing that's electron rich doesn't have its electron density anymore. It's a good point you brought up, but just work out the logic, right? So what would make it less reactive or more reactive? What do you think?
I think we make it less reactive then.
Exactly, right?
Okay.
So it's a good point you brought up, right? Jared said, like, what if he puts an electron withdrawing group, right? Automatically, anything with the electron withdrawing group is going to get much less reactive, right? Because it doesn't, the HOMO's energy level, I guess, will increase, right? Or the HOMO-LUMO gap will increase. Well, I guess it will lower the energy level of the LUMO. Or that part, I can't accurately say that, but basically it's going to withdraw electron density, which is not good for a diene, right? Dienes want their electrons. They want to be electron rich, right?
And you have somewhere in your notes, like the two different, like the ways to identify an electron donating group and electron withdrawing group, correct?
I think so. Let's see. One of these semesters. Give me a second. Or you could ask your question while there we go. Yeah.
I have like the rule I have for to identify them is just like having, if you have a double bond that's outside the ring, or sorry, a pi bond that's outside the ring, it's going to be electron donating. I'm sorry, electron withdrawing, because it takes away, like with resonance, it takes away electrons from the ring. But anything that has lone pairs, it's donating. And alkyl groups are also electron donating because of the lone pairs. But for halogens,
well, not because of the lone pairs for the alkyl groups.
No, for the oxygens that have
lone
pairs
for the
yeah. For the halogens, though, those are always electron withdrawing because of the electronegativity, right? Because they're halogen. Okay, that's always the case.
So halogens are electron withdrawing groups, just to be clear. But the way they affect, this is only for aromatic stuff, the way they affect directing effects is orthopara, and that has to do with the resonance of their lone pairs. But in terms of pure electron donating and withdrawing group, forgetting about whether we're dealing with aromatic, whether we're dealing with any compound, right? Halogens will always be electron withdrawing because of electronegativity.
So it's electron withdrawing, even though it's electron withdrawing, it's still orthopara when it comes to ES, right? Electron, is that correct?
For what? Halogens? Yeah, they're orthopara directing. They're they're deactivators, right? But they're orthopara directing.
And that's the only exception.
Yeah, to like in terms of directing effects, yeah, they're the exception.
Okay, thank you.
So guidelines for dienophiles kind of make this similar. Really, honestly, just check for EWGs. That's usually what it's going to be. Or one second. I don't want to sneeze in the mic there. I guess you could also check for electron donating groups. That would make them less reactive, but that kind of goes hand in hand. But yeah, for dienophiles, mainly it's check for electron withdrawing groups, more reactive, right? Maybe I'll just make a little note saying EDGs make dienophiles less reactive, right? And you saw that on one of the Actually, I think it was just on this 2019 exam that we pulled up. Yeah, it was 2019 exam. The one with the cool oxygen, double oxygen thing. But yeah, that had dienophiles, right? Okay. So let's move on to the next question. Where's this exam again? Okay, this one is, that's why I said, I was looking through all the exams, and this one, it was, the reason I want to go over it is because there's a good amount of difficulty here, right? I feel like, that's why I like Professor Bisco's exam. He puts the right amount of difficulty, and I like that. Same with Professor Andia, right? They don't really test for like, like, can you memorize a reaction? They test for, do you understand what the hell's actually going on, right? Okay. Frito crafts, we'll get to aromatics when we could talk about those when we get to question 4. Okay, so you guys take a few minutes to do this, right? Only hint, actually, I'm not gonna give you a hint because you're not gonna have me that you can't ask me questions during the exam.
It's because of conjugation.
Let's take a 2 to 3 minutes to work it out. I just want to give everyone a chance to work on it. You guys can keep still working on it. I think tomorrow I'm probably gonna be running some more screens. So there is going to be, I don't know what time I'll get in the lab, probably 8 or 9 o'clock. Actually, probably like 9 o'clock. So if I have my screen set up by around 10 to 11, around the afternoon time, I will be available to do any more review. Let me actually just check because I have a. There we go. Gotta make sure I have the key to the room in Marshak where I can actually meet up with people. I guess I'll open up to Zoom as well, but yeah, if anyone's around on campus around that afternoon time, I should most likely be available. I'll just confirm again, like around afternoon, like 12:01, right? So yeah, basically around 12 to 3, I should be free. Somewhere around that time. Like I said, I'll let you guys know in the morning. Okay, I think that should be enough time. Okay, so explain why compound 1 undergoes Markovnikov addition of HCl, while compound 2 undergoes anti-Markovnikov. So in case you forgot, he kind of already showed you the expected products, right? Markovnikov addition, quick orgo 1 review. You are forming the most stable carbocation, right? That's Markovnikov's rule. I mean, I know the book, whoever you're a professor for orgo 1 probably always tells you, oh, the H ends up on the positions with more H, but that's not really true because there's some cases where it looks like it might end up on the position more H, but the other one's more thing. So the best way to think about it is if you broke this bond, right? Where would there be a more stable carbocation, right? So in here you have a positive charge, right? This would be tertiary. If here you had a positive charge, it would be primary, right? So if we were to do this reaction, let's change colors here. Blue is too mellow. Right, so simple addition reaction, right? Your nucleophile, right? In case you even forgot, just going over this earlier, but in case you even forgot if you know how this reaction works, right? Just think about it in terms of what I kept saying over and over. Identify the nature of your reagents. This is a part of a molecule that's electron rich, right? Here you have a partially positive, partially negative, right? HCl, right? So most likely it's going to be a nucleophile, electrophile thing kind of happening, or protonation, really, if you want to think of it that way, right? So the place that has electron density is going to go to the place that doesn't. This gets its electrons, right? So even if you don't remember the mechanism, you could always logically work it out based off electron flow and where electrons are, right? So now you can do that. We get our intermediate that looks like this. Say the H is here, this is a positive charge. Now Cl comes in, right? And you get your product. So you just show the mechanism. But really is, I mean, once you do that, you're like, okay, how do I answer this question? That's where really you're asking, the question is really asking you to analyze the second part. So here was, I could just draw this as Cl, right? So now if we do the second one, right? This is where you could either draw both mechanisms, or if you instantly kind of notice what happens if you form a carbocation, right? So we have the cyclopentadiene at the bottom with this alkene here, right? So if we attempted a Markovnikov addition, same thing, electron flow, you get this. And now if we just look at purely at the intermediate, this is where the H is. This is a positive charge. We have a carbon, like I said, carbocations, they're always locked into their hybridization, right? So this is what's a hybridization at a carbocation.
This allows for easy conjugation. It kind of helps the system.
Well, it's sp2, right? That's what I was asking, but I mean, your point's about to come into play here, right? It's locked into sp2, right? We have other carbons that have pi bonds in them, and we have a cyclic ring at this point in the molecule. So what you always should do when you have a cyclic ring that's planar is check for aromaticity, right? So you have the p orbitals here and the empty p orbital here, right? We have how many pi electrons? 4, right? Is there any pi electrons at the carbocation? No, right? So this intermediate, just purely looking at this intermediate, right? What is it?
Anti,
right? So going from this step, right, this protonation in this manner, right? This is going to be very unfavorable reaction, right? Because essentially you're creating a very, very, very high energy intermediate. You know, carbocations always are, you know, higher energy than something neutral, right? But in this case, you're creating something that's anti-aromatic. It's going to be ridiculously high in energy, and this pathway will basically never be open, right? But now if you kind of look at what might have happened in the other pathway, right? This is kind of where you have to work backwards a little, right? Is this must have came from something that looked like this, right? This is kind of retro synthesis, I guess, right? This would have to have come in from an intermediate that there was a primary carbocation, because that's the only way the Cl can attach, right? So if this was a primary carbocation, right, we could say that, you know, the H ended up here, right? And if we deprotonated that H, right, we could kind of think of this as a carbanion, right, where you have the lone pair here. So this would be a carbanion, right? And in this case, if we had an intermediate that kind of looked like this, right, what would be what would it be? Anti-aromatic? Would it be non-aromatic? Would it be aromatic?
Aromatic.
Aromatic, right? So essentially we're doing a reaction through a pathway that has an intermediate that will be aromatic stabilized, right?
Wait,
and that
how is it aromatic though? Isn't there an H there? What happened to the H?
I said if we had an H and if we removed it, right, just looking at purely the carbon, right, it would look like
Oh.
a carbanion that looked like that, right? So I'm
Yeah.
assessing really the carbanion, right? So if this was a carbanion that looked like this, it would be aromatic stabilized, right? And that pathway, right, this going from here to here is a lot more favorable than the anti-aromatic pathway, right?
Isn't that carbon now sp3 though? Because it has 3 sigma bonds and 1 lone pair.
For what this
There with the where you put the lone pair, it has 3 sigma bonds there and it has a lone pair.
with the lone pair, right?
That makes it sp3, right? So it's no longer planar.
Let me think. So remember when we had this question, right? Furan, we said the same thing, right? Where was the other, what kind of orbital was the other lone pair in? This one. Because this was aromatic, right? But it has 4 electron domains, right? So what kind of orbital is that lone pair outside of the ring in if this is sp2 hybridized? sp2, it's sp2 hybridized, right? This furan ring, right? Because it's aromatic. So that means the other lone pair has to be in an sp2 orbital, right? So you could kind of think of that carbon the same way, that all these bonds are sp2 hybridized, right? That lone pair is in a p orbital, right? So it's not that's why understanding hybridization is kind of important, right? Is are the bonds like, yeah, there's 4 electron domains, right? But, you know, in the case of carbanions or those heteroatoms, right, that extra domain might be in an sp2 orbital. So it's a good point you brought up there, whoever was talking, right, is that it has 3 bonds here, right? But carbanions, right, we saw this too, same thing with here, right? If we add cyclopentadiene, the carbanion form, right, it's not shown as the H, right? But the H is still there, right? It still has the same thing, 1, 2, 3 bonds, but all those bonds are sp2 hybridized bonds, right? And the orbital is still the p orbital. It's in conjugation with the rest of it, right? So just remember that that's why hybridization is a little tricky thing to understand. That, yeah, 4 electron domains, you expect sp3, right? But when you have one as a lone pair, right, you could, you know, make it sp2, and the other orbitals, you just consider them sp2 orbitals, and the remaining orbital, right? Because if you had 4 electron domains, but you chose your atom to be sp2, the remaining orbital you have left is a p orbital, right? And that p orbital is in conjugation with other p orbitals, right? That clear that up? Everyone good on that? Why, like carbanions, heteroatoms, and everything, why the hybridization is sp2 in certain cases? Certain cases they'll be sp3, right?
I guess we're good on that, but I'm still not good on why it would be. Why is that related to it being anti-Markovnikov? Why did?
No, we
why is
didn't.
that
We didn't finish that part. I was just answering that person's question. I was just making sure everyone's good on the hybridization stuff, right?
Okay, yeah.
Okay, just to clear that out. So anyways, right, going back to this question, right, we're going to this aromatic intermediate, right? So you could say that this went through an intermediate that was aromatic. I guess if you really want, you could kind of break. I don't know if I would do this, because basically how I would expect this really to happen is while it's transitioning, you'd have the proton attack the carbon at the inside, because essentially you have, so I guess a good way to, I mean, I don't like doing this, but I guess a good way to look at it is the resonance structure, even though generally you wouldn't ever do a resonance structure like this. But if you were to, you know, just do a structure that looked like this, right? But what I would say really what's happening is at the same time as this electron pair is delocalizing, right, that proton is being attached to it, right? And the whole reason is because of this intermediate, right?
Sharuk,
Mhm.
could you say that it just undergoes a hydride shift to make that carbo?
Well, it wouldn't be a hydride shift, right? Because it's really just the pi bond pushing into the what's it called? Other carbon there, right? A hydride shift is when you full on move a hydrogen with 2 electrons, right?
Okay.
So really, you kind of have to work this backwards to see what kind of intermediate you get. And I guess, I don't know if, I mean, I think in this case, it'll be okay to do a resonance structure. I don't know, that's what he did too, but you could say it does a resonance structure that looks like this, but I would work it backwards and essentially say that you probably originated from an intermediate that looked like this, right? And then because of that, the proton is more likely to end up at, and then you just label your carbon at the end of the ring, because it would be aromatic stabilized in that brief moment of time, right?
I have a clarification question, if you don't mind.
Yeah.
So what I learned from Salami back in like last semester, and also from Bisco, is that the order of stability goes from primary to secondary to tertiary to resonance. Resonance is a lot more is like the highest, or provides the highest stability in that order. And so from this logic, I would say that, or can I say that, like for the next one, for the second part with the anti-Markov-Markov, the reason why it went for anti-Markov-Markov is because then the positive charge will end up on the tertiary carbon, which allows for conjugation to occur.
Yeah, I mean, it is conjugated, right? When it's in, you know, with all the rest of the orbitals, you could say that, but
because
yeah,
like my point is, if for the second one, if it went for the tertiary position or the Markov-Markov, then it would disallow conjugation to occur. And that's why it went for the primary, to allow for conjugation, because conjugation is more stable than tertiary. Do you see my point? Or what I'm trying to
yeah,
say?
I see your point, but like, I guess the only thing with that explanation is when you have like the other thing that looks like this, right? You have a tertiary carbocation that's stabilized by 2 bonds, right? And this is resonance, right? This is resonance stabilized tertiary.
Yes.
Yeah. So, I mean, is that why you were saying you wouldn't expect it to be more anti-Markov-Markov?
No, that's why I would expect it to be more anti-Markov-Markov, because then if the Cl is on the top carbon, the primary, and then it leaves a positive charge on the tertiary carbocation, then it would allow for resonance to occur. However, if the Cl and the positive charge switch positions, where the Cl is on the tertiary position, resonance cannot occur. So you're choosing resonance over the tertiary positioning, because resonance is more stable than the tertiary positioning.
See, my only issue with that is because when you look at, like, I completely agree with basically almost everything you said with the tertiary resonance stabilized, and that's why you expect it to be Cl, right? But the thing is, this intermediate will never form because in this specific case, right, we get anti-aromaticity, right? So, like, yeah, you would, you know, based off those rules, you would expect tertiary resonance stabilized to be thing, but like the whole point is this carbon never wants to be positive, right? the other carbon wants to be positive because that's, remember, in the second part of this reaction, the Cl is a nucleophile, right? In the addition reaction, right? That's what we did in the first step where we showed it made a tertiary carbocation, Cl attacked the tertiary position, right?
Yes.
Here, it wants to attack the other position, right?
What was the reason for that again, please, if you don't mind?
The reason for that is because in this intermediate as it is, right, we get an anti-aromatic intermediate, right? We have 2, 2, right? We have a carbocation locked into sp2, right? So that's 4 electrons here, and it's anti-aromatic, right? The other way, if we went the other way, right? Essentially, if we kind of looked at the, we kind of broke this off, right? This essentially came from something you'd expect to look like this, right? Where the hydrogen would be here. So then if we remove the hydrogen and only left this as kind of a lone pair, right? Right, then you could see this is an aromatic stabilized intermediate versus an anti-aromatic, right? That's the reason I wouldn't pick the tertiary resonance stabilized thing, because it doesn't explain why one intermediate is higher energy than the other, right?
So for the anti-Markov-Markov, the Cl adds to the primary position, and then simultaneously a hydrogen adds to the tertiary position, which prevents the positive charge or the carbocation from existing in that.
Basically, right? Because the more in this case, the more electron-rich carbon in the alkene is going to be the one that's closer to the ring, right? I guess that is a reason why you could draw the. So remember those questions with the dipoles, right? Where we did like something like. Actually, this is a perfect way to explain this. Like, remember we did something like this. There was like this. Where was it?
So
This. Give me 1 second, right? So remember we did this, right? And then we split the pi bonds, right? So think of that molecule the same thing. If we just looked at it in terms of a dipole, just this one bond, right? So now if we did a resonance structure, right, and we just push this here, right? You
It would be aromatic, yeah.
Yeah. So that's actually a better way to look at this then, right? You could do it 2 ways. You could do the retrosynthesis way and say that essentially it most likely formed from an intermediate. That is what we expect to be aromatic stabilized. Or you could say that the original molecule exhibits a dipole because it will be aromatic stabilized in its other resonance form. And that's why, right, now the next step would just be the carbanion, right, attacking. Right now you get protonated. Now you have a primary carbocation, which is, super reactive in this case, right? Cl will immediately come to it, right? So generally, like, your logic is perfectly fine. Like primary carbocations, we do not want them, right? But in this case, the pathway prefers the primary carbocation kind of pathway.
Only
right?
to avoid anti-aromaticity.
Exactly.
Thank you. Okay.
Yeah. This is why I like this question, is because it makes you think of a lot of these concepts, right? I don't know if you'll get something as difficult. I mean, he did make this, so there's a good chance. So that's why I wanted to do this exam particularly, because I just saw these questions and I was just like, this kind of goes over everything, right? So is everyone clear? Like, if you want me to explain one part of this again, speak now.
Could you just explain the second part? Because I still don't understand why the Cl made the anti-Markov-Markov. Like, I'm still lost on that part.
So if we look at just the molecule, right? I mean, there is the short way would just be to draw the resonance structure. I mean, this was just to explain everything, I mean, I don't know what he wrote on the answer key, but okay, hold up. Let me just see what he wrote on the answer key. Give me a second. 2015 exam 1. Okay. Okay, so he really did do the resonance structure. Okay. All right. So yeah, I mean, that's pretty funny actually. So yeah, no, he did the dipole kind of thing I was talking about, right? Where he broke it off into a resonance structure that looked like this one here, right? Let me circle it. I'm looking at the answer key right now. So he explained it the same exact way, more or less, right? If you looked at just like the structure itself, right, where you would expect electrons to spend their time, right? So if we got this structure, right, if we were just to analyze any resonance forms, right, like we did those dipole questions, right? If we push this here, the other resonance structure, even though generally you don't want to increase, formal charges and primary carbocations, but in this specific case, right, its resonance form makes an aromatic intermediate, right? Which means basically that this alkene, the majority of the times, the electrons spend their time near that carbon with the ring, right? That's because remember, resonance doesn't actually exist, right? It just tells you where electrons are and where they aren't, right? So when you look at the resonance, right, you'll see that you can you'll see that the electrons will spend most of their time at carbon. I should label these carbons, the red carbon that I circled here, right? Because it's going to be an aromatic stabilized species. And because of that, right, because that carbon's more electron rich, it will be protonated, and therefore the Cl will end up on the, I guess, the primary position, right? So that's how you would show it. Or you could show it the other way, that if you wanted to do the kind of retrosynthesis way, where it was you broke it down into the same kind of intermediate, right? I mean, we just went backwards in what we did, right? Is I broke it down into this.
Sure.
Yeah.
So just showing the fact that it'll be anti-aromatic if we try to do Markov doesn't, Bill. Like,
Well,
that's
you
not
probably
enough?
have to. That's why I showed the first one, because that pathway is very bad, and then you'd have to show that the other pathway is very good, right? So that's really what this question's asking is why one pathway preferred. But the only way you can compare both pathways is when you draw them out, right? And I'm looking at his answer sheet here, and he says the same kind of thing where he drew out both pathways. He said the one we first formed is anti-aromatic, and then the one we formed the other way, right, is aromatic, right? And that would be the reasoning for this question.
All right, and this might sound silly, but I just want to ask it anyway to make sure.
Yeah.
When he gives you a question and says explain, he doesn't mean like give him a paragraph.
No,
He means like
you want to show like electron flow and resonance structures generally, and then he'll be able to see that he knows what, like, just briefly describe it in a sentence or two, like, all right, this is anti-aromatic, this is not a favorable pathway, things like that, right? So as long as you can logically prove to him, right, if you want to write a paragraph, go for it, but like if you can logically prove to him why it goes one way or the other, and the main kind of substance is all electron flow, right? That's what he's really kind of worried about in this question, or looking for, is like, do you understand where the electrons are? And that's why I did this dipole thing, was to show you that this alkene, right, this entire structure really, right, in that alkene part, right, the electrons spend most of their time at the red carbon, because that would make it an aromatic stabilized intermediate or resonance structure. And because of that, it goes to anti-Markovnikov, because the proton will end up at the place there's already electrons, right? The Cl isn't going to go to something electron rich because it's a nucleophile, right? So just show the electron flow, show resonance structures, and just briefly describe them. If you want to write a full paragraph out, as long as it makes sense, write it out, right? But usually showing electron flow is enough, right? And on the other part, he just wrote tertiary carbocation is most stable in this case, right? Which makes sense because, this is a Markovnikov addition. And the other one, you're really just proving why it wouldn't go Markovnikov. And the reason is the Markovnikov route makes anti-aromatic. So then you check the anti-Markovnikov route, and that goes aromatic. And if you show all the electrons, you'll see that it ends up there. So the only thing he did different was he actually made the Cl attack first, which makes sense because the primary carbocation is probably more reactive than the carbon ion. So that's the only thing he kind of did different than what I did, right? But as long as you show that really what he was really looking for was this structure, it looks like. And I got that basically two ways. One by showing the dipole, right? And the other by going backwards and seeing what the kind of synthetic intermediate it originated from, right? So whichever way makes sense, as long as you can, give him enough information to, make sure he knows you understand, you're good, right? Like I said, this is a almost 6-year-old exam, and generally it seems like he, actually, I don't know. With Professor Visco, maybe he'll put up a question like this because, he really loves the organic chemistry, and he wants to make sure people are taught it properly. Okay, so let's move on to the reactions question. I think there's one here that we're not going to do. Yeah, so it's the sigmatropic rearrangement. Actually, no, that's an electro. Yeah, no, that's okay, so there's going to be one we ignore here, but everything else we're going to do. So I'm going to grab the first 3, and you guys can take, okay, let's do the first 4. And I'll let you guys try those out. And if anyone has questions while other people are trying it out, feel free to ask.
Hey, sure. Usually we'll see ZnHg, HCl, and then heat too, right?
Yeah, but I mean, like I said, it's not too important, right? It's not like the reaction will not occur without heat. It'll occur just very slowly, right? So like in this case, if you didn't forget to write it, just still go forward the reaction as you expect it to. Right, so one thing just to kind of let everyone know, all this kind of schemes you guys see in your organic undergraduate organic level classes, right, is some things might be missed, like none of these ever have the solvent in them, right? So like things that you see in papers, right, they will tell you the temperature, the equivalence, the solvent, and everything, right? Here, it varies on your professor, right? It's kind of just looking at the main reagents doing the reaction, right? So if in case here, whether there's heat or not, this reaction will occur, right? It just will occur a lot slowly without heat, right? But there are certain reactions that just wouldn't occur at all, right? I think back in 2015, it didn't look like he gave those kind of questions where there was no reaction. But now he might. We don't skip the second one. You guys know the second one. It's a allylic bromination, right? So that's why I said knowing the structure.
I don't want to be like.
Sorry, you're breaking up. What's up?
I'll be embarrassed, but
don't worry about being embarrassed.
But I might as well ask. Can we think of that as kind of like a HBr, with that the structure next to the Br being, the H?
I'll do you one even simpler. Just thinking of it as this. Oh, I did not show up on this thing lagging. Yo, can you all see the screen? Okay, that was weird. All right. Just think of it as this. Br radical. That's it. You don't even have to think of it HBr or anything. That's what I said whenever you see NBS, right? It's equivalent to just having a Br radical. That's the whole point of it, right? Is that halogen abstraction is super simple. So yeah. Because the issue with HBr, right, is you're gonna get what's called hydrohalogenation, right? you're going to have the hydrogen attach as well as the bromine, right? So when you want just pure radical bromination or radical chlorination, right, you're looking for sources that have just pure bromine or chlorine, right? So HBr, what you guys saw the radical version was HBr with some sort of peroxy acid, not peroxy acid, alkyl peroxide, right? So something like, oh, and you have like, I don't know, one common one is I think acetate one, any sort of peroxy acid, right? This is not peroxy acid, I don't know why. Alkyl peroxide, when you have the O single bond O, right? That is anti-Markovnikov addition of H and Br, right? Because it goes through a radical pathway. And when you have just HBr without the peroxide in there, right, then that's a Markovnikov addition. That was something from Orgo 1. But whenever you see NBS, right, which you learned in Orgo 1 and relearned here, which is why he brings it up, right, is all you could think of that as Br radical. Same thing when you see Cl2 in some sort of radical reaction, it's the source of the Cl radical. Br2, the source of the Br radical as well, right? Bromine gas and chlorine gas, for the most part, people don't really like working with them because they are toxic, right? And it's hard to work with, especially bromine, right? That's why NBS was developed, because specifically for allylic and benzylic radical reactions, right? It's a much more, or I should say, much less toxic reagent to work with, right? NBS, I mean, if you want to do radical bromination, sure. I mean, I've never worked with it. I mean, I don't know if anyone, maybe we have it sitting in our fridge. I mean, I'm sure some people use it, right? Like different groups do different stuff. Like Professor Bisco's group, which I work in, we do organometallic catalysis, right? We basically use stuff like palladium, right? Which is coordinated, like I guess in our case, it's DBA, dibenzyl acetone. I forget how the structure looks like. I shouldn't really forget, but it's like coordinated with different things. I'm just drawing a structure here, just like this. I think it's actually, this is a pH, pH 2. Maybe the structure's wrong, but either way, it's like coordinated with different groups to like give it a different, what did I say? Coordination number, like an amount of electrons, something called the 18 electron rule. And essentially those catalysts, right, what we could do is could take something like a tin, right? This is like a Grignard, right? This is going to be electrically negative, and you could bind it to other stuff that normally you couldn't do carbon-carbon bonds with, right? So now we could do sort of this alkyl tin bonded to this aryl position, right? I mean, this is the reaction you wouldn't really do, but you know, the point being, it's good for carbon-carbon bonding. And there's also carbon nitrogen, carbon nitrogen, but that's the kind of chemistry we focus on. So, you know, if anyone is ever interested in that, really, if you're interested in or like wet chemistry, right? The main thing is you got to make sure you do well in this class, and then also your Orgo lab class at the end of the semester. I was talking to other people in the group because the grad students need they want you know, people to help them, or they want people like undergrads to mentor, right? So if you're looking to do like independent study or honors research in a wet lab, I'm sure Professor Bisco would be willing to, you know, talk to you or maybe let you in the group if, you know, you do well in this class, and also organic lab, because that's the main thing. You got to make sure you actually have those technical skills. But I don't think that should be too big of a deal. Like if you did well enough in this class, you seem interested in the work we're doing, like I said, at the end of the semester, just ask Professor Bisco, you know, it never hurts to ask, right? That's how I got it, right? And now I'm about to get into hopefully a PhD next fall. Yeah, I mean, it depends on, you know, your interests, right? So anyways, let's go over these problems. So the first thing, right, is we have amalgamated zinc with the hydrochloric acid. So it's amalgamated zinc in acidic media, right? What kind of reaction is this?
Clemenson?
Reduction?
Yep, Clemenson reduction, right? So what kind of changes do we expect when we have a Clemenson reduction? Or what, well, not really what changes, what kind of functional groups does it interact with?
So the double bond, I was just gonna disappear and it's gonna be.
Yeah, the
Yeah,
carbonyl
it's gonna be
carbon,
2
right?
H's.
So essentially it just kind of chops off that carbon, right? And makes it into 2 H's, right? So just check, like if we had another group here, right, this reaction, right, would reduce both of those groups. So really any carbonyl or any acyl group, actually no, in this case it'll be a carbonyl since it's a ketone. So the product you expect, right? Really, like he's not, I don't think he'll take it to that level, but technically, right? Oh, sorry, it should be ethyl. Oops. So that's your product, right? He said he won't ask about this reaction. I'm pretty sure you guys learned about Clemenson. He's probably
You won't
talking
ask about the NH2,
Yeah.
NO2 reduction, not
Yeah.
Clemenson.
Yeah, that's what I'm pretty sure a lot of people said, right? Was the NO2 to NH2 reduction. But technically just
That's in Chrome, right? You showed us this yesterday.
yeah, I'm pretty sure I went over this yesterday. But either way, like somebody might have been thinking about it, right? Since we are in HCl and we have an amine there, there's a good chance this amine was probably protonated, but you don't have to worry about that in your answer. He's really just looking for the Clemenson reduction. But like, if you want to be very specific, right, it wouldn't be wrong if you protonated this amine, made this a NH3. Just things to think about, right? Because we are in acidic media, we had a basic group there, right? So NBS, so this one, we went over something similar the other day, but I talked to Professor Andy about this too, right? This will actually have 2 products, right? And this has to do with the radical pathway it kind of takes, right? So kind of cutting, I'm not going to go through every, the propagation and like initiation, propagation, and termination steps, right? I'm going to go straight to the kind of intermediates we're looking at here, right? Is eventually, hopefully everyone remembers, at a certain point, you're going to get an intermediate that looks like this, right? And then we have our methyls, and we have, oops, right? So that's how we get. So we're all good that carbon radical that forms, right? The thing though is, right, when you form this, right, since this is a allylic radical, right, it's going to undergo it's going to undergo delocalization, right? So you could have a fishhook arrow showing this, and then this will be here, right? And basically there's an equal chance of each radical, going through the rest of the propagation and termination steps, right? So draw that back in red, right? You will actually have 2 products because you can't really say which one is more major or minor than the other, right? And I asked this to Professor Andy and said basically, yeah, when you go through a radical pathway, if you have like an allylic radical, right? You have to draw the product out of both pathways because it's hard to determine which one is major or minor, right? So in this case, you have 2 radicals that looks like this, right? And then the next step is that just interacted with the BR radical. So really, you have products that look like this. Pretty sure there should be 2 products. I'll check the answer key right after this, but pretty sure he would have drawn 2 products as well. That just did this problem like a few days ago. And okay, that's a 5-member string. I can't draw it a little better right now, but So here we have
I don't know if you know
BR.
his pattern.
Sorry, what's up?
I don't know if you know his grading pattern, but on these on these major product questions,
Mhm.
does he get partial credit? Like maybe if we give only one of these structures instead of both?
Yeah, he'll give you 1.5 points for those, right? If there was 2 major products, right, and you only drew one, and you drew the correct one, right, he'd only give you half the credit, right? So he's pretty generous with the partial credit there, right? And as far as I know, I don't want to say anything too early, but usually I've seen he curves. So you guys also have that going for you.
But I'm confused now because on some of the answer keys he has,
Mhm.
he gives you like a ortho para addition, and it's like empty, so you can add to either position. But major is usually the para, right? But he does para and then plus another structure. He puts ortho.
Okay, after we're done with this exam, show me that problem.
All right.
Sharuk,
Yeah.
sorry. So NVS is a radical bromination, as you said, correct?
Mm-hmm.
And then you put the radical on that carbon because it's just next to the double bond, or is that the reason why you put it there? I'm still confused on that.
Yeah. So if we look at all the other carbons, right? Remember, what's the thing about NBS or really bromine in general when it comes to radical reactions over chlorine? What does it do?
Well, I think as you said, it's able to resonance. It's able to create a resonance structure, and you want to find the secondary carbon that has
Well,
that.
kind of, but it's selective in the position it chooses, right? So just by looking at the structure, I knew it was going to be at this position. Why? Because let's look at the other carbons. There's no hydrogen here for abstraction. There's hydrogens here, 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 and here, right? But the one I circled blue is the best one because it's next to an allylic position, right? And NBS specifically, right, always, selectively brominates at benzylic and allylic carbons. That's just a thing you need to know about the reagent, right? So the rest of these are all secondary, right? But this is secondary allylic. So this one is going to be the most selective and most readily available for bromination with NBS.
And
right?
if we had if we had two spots between a benzylic or allylic, like if we had 2 spots, would it matter which spot we chose, or
What do you
not
mean
really?
2
They can
spots?
resonance. Like say if you had a 6-ring carbon, and then you could have like another spot that's allylic, and then there's another spot that's allylic, like if that makes sense.
So like you had a 6-membered carbon and you had this.
Yeah, and then like see, now there's like 2 spots for where
so
you
then
could
if
have
you
a
had something
radical.
like this.
No, like
one sec.
before.
Here.
Yeah, like now you have 2 spots in a sense, I guess.
That one would be hard to tell. Like I said, for the scope of this class, you won't give me a second, Abigail, but you won't be getting something where it's like hard to choose one spot over the other, like the previous questions we did, right? This one, like you bring up a good point. Technically, this position and this position, right, and this position are all allylic. And it would be hard for me to even say which one, but I would probably, if I'd have to pick one, probably that one, just because when you do the other product that forms, right, it's not going to be it's going to lose a double bond in the ring, which is going to make the ring a bit more stable, right? So that has to do this with ring strain, right? And then on top of that, it's going to make a tri-substituted alkene as well, right? Like I said, that's just because I've done this enough where I'm thinking like that, but you guys don't have to worry like, yo, oh my God, don't worry about, it's great that you're thinking about that. I love that, people are taking it to another level and like thinking that those are the questions to ask, right? Yeah, in this case, yeah, you'd work through that logic that you'd get an alkene that looks like this, and that's tri-substituted. You're also removing the strain on the ring, right? But the reality is you'll probably get a good mixture of products. But I would probably expect the product where you have a tri-substituted alkene to be the most major out of all of them, just because it's the least strained molecule, right?
Okay, thank you.
Yeah.
That kind of cleared that up.
Yeah, but like I said, he's not going to ask questions like that. But it's good to think about, right? All little things. How do you do that? That's why I said at a certain point, like all the stuff that you guys do is to a degree essentially like qualitatively analyzing electron flow. But after a certain point, you have to experimentally do it to prove one over the other, right? And generally, most of the stuff he does, as far as I know, he always takes examples from the literature, right? You'll be able to finish this exam. We're just taking time since we're reviewing each question and I'm going through stuff in detail. You guys can't be doing this on your exam. You're going to have to, time manage. You guys have an hour and 50 minutes though. I think that's plenty of time for this exam. Like I said, I'm going slowly because I want to make sure I explain everything, but at the point you guys have reached now, you should be, able to do these relatively quickly, right? So that was the products we formed there, right? Because that was the allylic position and it's identical resonance radical that forms. So we get two products. So it would be this. And as someone asked before, if I only drew one, what would happen? You would just get half the credit, right? Okay. So next one is a Diels-Alder reaction, right? So what's the first thing we always do when we see a diene that's in S trans?
Make it cis.
Yep. Whoops, that's the wrong color. So let's go down here, right? What I said, leave this part staying, draw your double bond that way, right? That's a kind of surefire way you'll never mess up your double bond placement. There's no groups there. There is a OME group here, right? So now let me just redraw this form that we kind of always seen it in is OME, and we'll also rearrange the dienophile, right? So can we just go ahead and do it as reaction, or is there something we have to consider before we do it?
Partial positive and partial negative.
Right, so we have an unsymmetrical diene and an unsymmetrical dienophile, right? Which means that there's going to be one part of it that's going to be favored over the other or more electron rich, right? So in the diene, I label this 1, 2, 3, 4. Which carbon do you expect there to be the most electron density?
1.
1, right? We went over this when we did this, right? A quick way is outside groups, opposite carbon. Inside groups, carbon next to it, right? So here, if you wanted to see the resonance, it's going to move like this, right? And it would essentially just have a partial negative charge here. Here, dienophile 1 and 2, which one is more partially positive?
2.
2, right? Because it resonates with the double bond, right? So now if we want, we could flip this. I will just flip it by drawing it this way. Now we could do our Diels-Alder reaction, right? Partially positive to partially positive, double bonds. Now the only thing you have to worry about, right? And I don't remember if I went over this during recitation. I do recall doing it during one of the review sessions, in case for some of you watched the video. But whenever you're doing, let me just bring this up before we draw the product, right? So whenever we did it with like a cyclic thing, right, and a diene, right, we got this, right? So maybe if I draw these bonds with a different color, point out what I'm trying to get at here, right, is these are inside groups, right? Oh, I'm sorry, there was somebody who I forgot to answer your question. When I finish this, I'll answer that. But you notice how these are essentially, we can consider these inside groups, right? The kind of rest of the ring, right? And it's pointing upwards, right? So when you have non-cyclics, the same logic is applying, right? It's, you just have to make sure you draw it in terms of wedges or dashes, right? So the H's here, right, will be pointing downwards, right? Or on a dash, however you want to draw it. Same thing here, the H is on a dash because it's outside. So if this OME is an outside group, what do you expect it to be? On a dash or a wedge?
Dash.
Dash, right? So just be careful when you do the unsymmetrical deals alders to make sure you have your kind of directional stuff correct, right? So now we could draw our product. So we could start with the 6-membered ring. Right? So this is where our new alkene forms, right?
Wait, why is it a dash, you said?
It's a dash because if we look at it in terms of a cyclic, like if we did a cyclic diene, right? The inside groups, which is this part of the rings, go upwards, right? They form that bicyclic that looks like this, which means the hydrogens that are technically, we can consider them outside groups, right? They will be pointing downwards, right? Or on dashes, right? So the same thing applies is we don't have the rest of the ring, but outside groups will end up on dashes below the plane of the ring, right? Inside groups end up on wedges above the plane of the ring, right? That clear?
You said
Whoever
outside
asked.
was what? You said outside was what was dashes and inside was wedges?
Yeah, so give me a second. If I did this plus this, right, and I drew it all in a 2D model, right? What this would look like would be CH2, right? 'Cause now we're looking at it from a bird's eye view, right? In this way, we're looking at it from the side in a 3D view. If we looked at it from the bottom up, or sorry, from the top down, right, bird's eye, you'd see the CH2 pushing upwards, right? Because that's the ring that's coming above, right? Which means hydrogens on the dash. So that's why outside groups are on dashes, inside groups are on wedges, right? This OME is an outside group. That's why the OME here, you'll accept on a outside group, right? And how about the ester? Is it going to be on a dash or is it going to be on a wedge? Why is it going to be on a dash?
Because it's outside.
No, that's on the diene file.
It's on the right side. That's why he told us it's on the right side. It's considered to be outside, and so it's considered to be a dash.
He said that for diene files?
Yes, I
Wouldn't
mean
we
that's the
also
way
have
he
Estimate,
explained
so
it.
it's
Oh, if you,
fine.
okay, I would just say because of endo preference, right? If you thought of it, same kind of stuff, it would be by being down, it would be more in that endo position, right? But that works too. It's probably easier to think about. But yeah, it's going to be on a dash as well, right? It's going to be below the ring. Like same thing if we did it here, right? Like if we did this with the, oops, sorry, this is getting a little too messy here. But if we did this with the OME here, right? We expect this to be endo, right? Endo is below the ring. Same thing here, right? You just consider, even though it's not a bicyclic, right? It will be closer to the pi bond because of the transition state that way, right? What are we drawing here? Should be this, I think, OME.
So I have a quick question. I got the same answer as you, but like upside down, like the wedge, I mean, the dashes I had
Mhm.
on the other side, like on the
So-
top and the right side.
So did you draw, let me just make sure if it's what, did you draw something that looks like,
So like in the top middle carbon of the cyclo, that's
is it
what
on
I
a wedge or on a dash?
on a dash. They're both on a dash.
I guess that would be the same.
Yeah, that's what I got. So I don't know.
You just flipped it over.
No, it's because the way I drew
mean-
it, my diene had the O and the methyl group on the top side, not the bottom side.
Yeah, so if you
yeah.
draw it, probably you drew it probably like, 1 second. Like this.
Yeah, that's what I got.
Then the other way would be this. Yeah, it would still work because even if you cut this in half, right, you can't differentiate whether essentially you're just kind of
Like flipping it.
flipping it. Yeah,
Okay,
right.
gotcha.
How do you know if it's if like on the diene file the the group is pointed to the right or to the left when you rotated it? Like the OME, how do you know it's pointed to the right and not to the left on
I'm
the
sorry,
top
this
carbon?
should be this one.
Yes, yes. How do you know if it's to the right or the left?
Just flipped it. Right? It's planar, right? I mean, you could draw it this way, but it doesn't really matter if you draw it this way, right? It's this is gonna be sorry, I drew it this way, right? OME, right? It's literally just flipped on the other side, right? It would just prefer to be outside if it can, right? Because it's going to favor that transition state, the endo transition state.
And it's dashed because of the endo preference, like you said, yeah.
Yeah, or
Got
you
it.
know what he said with the outside thing, that works too. But
Endo's more
yes,
safe.
yeah. Yeah, so don't draw it. Yeah, even if you did it the other way where you lined it up, yeah, it still works out to be dashes. So never draw it on the wedge then.
Sharuk.
Mhm.
So I'm sorry, I know this is going way back to the beginning, but I'm kind of confused why you took the dienophile and then flipped it. Is it because of the hydrogen that's on the end of that other double bond? It makes it trans?
Sorry, you mean here?
Yeah, for the deal, like at the beginning. No, I'm sorry, not the dienophile, the diene.
Oh, yeah,
Yeah.
because it's trans right now. So we leave one part the same and we flip the other this way. We conform the other this way to make it as cis. Right?
Yeah, no, is it because at the end of that double bond, there's a hydrogen pointing, I'm assuming, downward?
The hydrogen pointing on both sides, right?
Oh,
It's a terminal
Okay.
alkene, right? So
okay.
when there's no groups, when there's actual R groups, right? Like I said, then you do the mirroring thing. So if there was an alkyl group that way, right? Then this is a mirror, right? So then you draw it inside like that, right?
Okay.
But when it's just purely terminal with only H's, right? It doesn't really matter, right? Because you can't distinguish between the H's. But same thing if you had two alkyl groups, right? It wouldn't matter because they're both methyl groups.
But we
Right.
would still rotate it because it's still trans.
Exactly, right? So you always have to do the rotation.
Gotcha. And then we flipped the dienophile because of partial positives and negatives.
Yes, right. So we want to make sure we line up the negative and positive ends with each other. And like
Gotcha, thank
someone,
you.
the other person did, they said they did it top, they did it like a line like this, but they just got the same answer, but rotated the other way. And that's perfectly fine because you can't really differentiate these two carbons from these two carbons, right? So as long as all the logic works out, you'll be fine, right? I mean, as far as I know, Professor Bisco doesn't really make mistakes on like grading and stuff like that. So, and you know, you're always free to send him your exam if you think there's an issue with it, right? But he's always very fair with the grading. He gives partial credit and there's curving, right? I think as far as I've always seen, he covers everything pretty extensively in lectures. So I like him and Bozon's lectures because they do it by hand, right? As opposed to like slides.
Professor, I'm sorry, Sharif.
Yeah, what's up?
Sorry, I have to leave now because I have to be at work at 6 in the morning. So I'll just, are you gonna close the recording right after the recitation today?
Yeah, whenever we finish this exam, I'm just gonna let it convert. But it'll be up late at night, probably at sometime or early morning if I go to sleep right after.
Okay, thank you very much.
Yep.
See you on the exam day. Bye.
Take care. Okay. ME. We're gonna take a break after this. I need to get a drink. What am I missing here? Okay. All right, so this was Hno3 H2so4. And like I said, when you see the equivalent stuff, it just means whatever amount of equivalences is, or if it's excess, right? Excess means as many positions as you can. One equivalent or etc. means he's essentially trying to only do this reaction once at the best position possible, right? So if we look at this ring, we have two aromatic rings, right? It's a biphenyl. Yeah, right. So you have a biphenyl thing here. So you have you have essentially 4 positions where you can do this. What reaction is this, by the way?
Nitration.
Nitration, right? And I'm not sure how long it takes him to grade exams. Probably within a week. It's funny, when I used to grade exams, like this was back in like 2 or 3 years ago. So for Professor Nobleman's class, because I did all his grading, I would do it the night before I told people how to hand them back. Oh, good times. Anyways, where's
I call that. It's overworking.
yeah, I mean, it's whatever. That's I mean, I had a week to do it. I was just lazy. Yeah. But the thing was, I had a system and I'd make sure I would, like, a lot of it was multiple choice anyways. So like it was easy to grade and then the rest would just finish it off by hand. But, you know, maybe
Multiple
rarely.
choice for organic chemistry?
Yeah, I mean, Lakshman does it too. And so does Boson to a degree.
Damn.
But anyways, let's label these. Okay, let's A, B, C, D, F, G, and H. Which position do you expect the nitration?
A or B.
A or B, right? So reason for that, right, is let's look at all the groups, right? Here, so remember, you got to consider each part of the ring like a group, right? So this is a group, right? This is a electron withdrawing group, right? That does not control the directing effects at all, right? You can kind of consider this entire thing also another electron withdrawing group, right? Because it's a biphenyl, right? Yeah, I guess it would be electron withdrawing because of the pi bonds. Once again, doesn't control directing, right? Now you look at this here, you have a electron donating group. This is going to be the best directing group here compared to the rest of the groups here. So now, as people said, it's going to be ortho or para, right? Para is already taken, can't nitrate there. But here's the thing. Doesn't matter which one you choose, but don't nitrate both of them, right? The phenyl group is, it should be a deactivator. I mean, it's hard to, the way I think about it is that it's conjugated with the other ring, right? So you'd expect electron density to leave, right? But at the same time, you could think of it as a giant R group that is electron rich, right? So that's something I'd have to look up. Yeah. Anyways, just nitrate one of them, right? It doesn't matter, right? We'll just pick the top one. Why not, right? But don't pick both of them, right? Because it specifically says here one equivalence, right? So if you did a dinitration product, probably wouldn't get any points at all, right? So make sure you only nitrate once. That was the whole point of mentioning one equivalence, right? You know what? Just since we're just right next to it, I'll just add the next question before we take our break. We'll take like a 5-10 minute break too.
So just to clarify, so if that had excess, there would be 2 of those?
Yeah, if it was excess, right? If you did get excess, then you'd probably just nitrate. I mean, reality is you could probably, nah, you'd still just only nitrate those 2. Yeah, if it was excess, I mean, yeah, I would just nitrate those 2. I wouldn't really see any reasoning to nitrate the others because this is still controlling all the directing, right? But anyways, the answer, because it's one equivalent, is just one nitration. But excess, yeah, then nitrate all the positions of the strongest activator, right?
And we should only like put it on one place, like show it like that, because it's technically symmetrical.
Yeah, right. So if you drew it, by the way, yeah, just a good thing you pointed that out. If you drew it like this, right, it's still correct, right? It's a symmetrical molecule there, right? You can't distinguish between A or B, right? I just drew it on the top because it's easier to draw there. But if you drew it on the bottom, it's still fine, right? The rest of the molecule is still the same, right? A and B are identical carbons in this case, right? Identical ortho positions. If I had something like this, right, if I had a methyl group, let's say at that carbon, then where would it nitrate, A or B? Think about that.
Sorry, can you repeat that? If you
If-
had
B.
If I had a methyl group next to A, would it nitrate at A or B?
because of steric hindrance.
Yep, right. So it would be B, not A, right? Because this is harder for the NO, it's harder for this alkene essentially, right, to attach a group, right? It's too much steric hindrance, right? But luckily you don't have that. But if you did, then you'd only have one answer. Okay, so the last one was this CH3 NO2, right? And then it was a Cl2, AlCl3, one equivalence, right? So if I label these A, B, C, and D, this is a chlorination reaction, right? Where do you expect the product to be? A or B, right? They're both identical, right? And the reason being, this is the strongest activator, right? This nitrogen and nitro groups are the strongest deactivators. They're extremely electron withdrawing. Alkyl groups are weak activators, but they will control the directing effects, right? So A versus B, they're both equivalent since this is symmetrical. It's a 1,4 substituted benzene ring, right? So the answer would just be, I don't know, let's put it there. Right. Okay.
So, sorry, one last thing.
Yeah.
This is in chapter 18, correct? Or
Yeah, this is chapter 18 stuff.
okay, that's it.
Okay,
Thank you.
so let's take a break. Everyone should, been doing this for like an hour or 2 hours, whatever. So everyone grab some drinks or something. Or I don't know if you want to leave to sleep. Feel free to. Just 1 second. There was a question way before that I meant to answer. Who was it? I think it was Abigail, right? Yeah. So why does the radical add to that position first, and why didn't the BR add? So was this when we were doing this bromination? I don't know if Abigail, yeah, you're still there. So what do you mean by the benzylic positions?
Where on the bottom left, there's two methyls, and those are benzylic positions, no?
No, so a benzylic position, to clear it up, right, is any position that is next to a benzene ring. So this is a benzylic position, right? It's one carbon away from a benzene ring, right? That would just be a quaternary carbon, right? So anytime you see an aromatic ring, like you have all sorts of alkyl groups on it, right? Isopropyl, etc., right? These carbons that I'm circling in orange, right? One carbon away, right? They are the benzylic positions, right? And one carbon away, as we went over, I think I went over this the other way. If you had like long molecule, right? Something like this, right? This is the allylic positions, right? One carbon away from a pi bond, right? Who was asking another question? Okay, so I'm gonna go grab a drink and I will be right back. Okay, Christopher, to answer your question, could you say that because the nitro is meta-directing and methyl is ortho, para-directing there? Yeah, I guess you could say the directing effects stack in the degree that they have overlapping positions. But the best way to always thinking about, like, to make sure you never kind of like avoid situations where you kind of think like that is that the activator always, the strongest activator always controls the directing effects, right? In the cases where you might have multiple activators, right? So if you have multiple activators where their effect stack, then yeah, that position's preferred, right? But the directing effect will like more or less always be controlled by methyl group in that case, right? So always give priority to the strongest activator, right? Don't really worry about the deactivators too much unless you only have deactivators, right?
I'm sorry, are you talking? Because I can't hear anything.
No. I was just answering that question. We'll resume in like 3 minutes.
All right.
Yeah, I don't know if anyone does fantasy football here, but I just beat your professor this week, and I matched up with his team this week. That's fun.
Does that guarantee you a top spot for your PhD program now?
You
I
play
don't know about that. Maybe that might affect it. No, he was undefeated in our league.
You play for money, homie?
Yeah, we have a big. Well, it's not really a big pool. It's just within the lab groups, and it's a couple of people. It's like 12 people.
Mans was playing for his tuition.
I guess. Yeah, I mean, I have some pretty bad receivers, but I just managed to overperform. Really, it's kind of lucked out. Really. Anyways, okay, let's get started. Well, so yeah, the questions we're gonna skip. There's gonna be one from this, which is an electrocyclic reaction. And question 7. So really, all we have to do is whoa, what the heck? Oh. Okay, now 5 is fine. 6 is fine too. 7 we're gonna skip, and 8 we're going to do as well. Let me just see. Yep. Okay. I might have done 8, but that's fine. 6 is the orbital one. It's still a cyclo addition though. So I don't know actually. I mean, it's still a cyclo addition. It's really just asking about the orbitals. So we'll do it. It's nothing you guys haven't seen. It's just kind of different than what you might have seen. Yeah, it's still it's not a Diels Alder per se, but it's, I mean, kind of is. It's a 4+2 cyclo addition. No, I didn't review another exam. I just kind of did exam questions in between the recitations. So like all the recitations, the way I do the lessons, even back when I did it in person, is I always do it per chapter, right? So that way, that week you learn about that chapter, and now that you have recordings, right, you can go and, you know, review everything about one chapter, right? And then, like, you know, tonight I had time for exam review. I don't know when your next exam is, but we'll see if we could do another one. Okay, what's the next question? Another Diels-Alder question, right? It's not going to be posted on Blackboard. It's posted on my OneDrive. Someone can link them use the second semester book. I have that in my OneDrive as well. So the first semester book goes up until chapter, like the IR chapter, I want to say, or not even. The second semester book covers aromaticity, IR, NMR. I'm looking at it right now, electrophilic, aromatics. And yeah, it covers everything except like the biochem stuff. Yeah, so use Orgo as a second language, second semester, 4th edition. It's in the OneDrive. Okay, where were we again? Diels-Alder question? Yeah. Oh wait, I didn't post the questions, so we'll just do them together because it's done. So we have this, plus we have, oh, I drew that wrong. Okay, so we have this Diels-Alder reaction, right? We don't really have a, we have an inside-outside group situation for that, but essentially we could say they're both symmetric. Oh my God, thank you for pointing that out. Plus that would be completely wrong. It should be this, right? I drew 5 bonds to carbon. Never do that. But thank you. This, and this, right? And for the most part, we could say this is symmetrical. We just have to be concerned about the inside-outside group situation, right? So now if we draw the base cyclohexyl ring, then we get cyclohexane ring, right? So the methyl groups, the top one, is it going to be on a wedge or a dash? Dash, good, it's an outside group. I could just write that as ME. And then what about the bottom one on a wedge, right? ME, right? And now what about this entire kind of oxygen 5-membered ring?
Dash.
Dash, right? It's going to be pointed downwards and it's cis, so it's both on the dash. Oops. And that should be the product. Yeah, so dienophile going downwards, right? Inside, outside groups on the right positions, right?
And then can we also have the methyls switching their stereochemistry as well?
Well, I mean, you would just be flipping it, right? But they would always be trans to each other. That's the key thing here, right? They can't both be on a wedge or they can both be on wedges or they can't be on dash. If you flip this entire thing, right, it would still be the same thing, just looking at it from the other face, right?
But if we flip over, it won't have endo technically, will we? Because the other
yeah, I guess
added-
it would be coming on a wedge, right? That's what I was kind of worried about the other situation.
like maybe we could just have another product where the methyls are just stereochemically just opposite to each other.
Like, what do you mean?
Because it won't be in enantiomer technically, but the methyl on top can be also a wedge, and the bottom can be a dash instead.
Yeah. And it wouldn't, yeah, I mean,
So technically,
the main thing is, like, if I look at this sideways, right, But the thing is, there's symmetry, so it wouldn't matter if you which one you drew, because then it mostly has to do because there is symmetry, right? Because if the top one was on a wedge, right, and the bottom was on a dash, right, all that would mean was that the diene was arranged like this. Oh, sorry, it was arranged like this, right? So you could, and that would still be the same product, right? You wouldn't be able to differentiate between each of those, because if you look at the rest of the thing, it's a symmetrical object, right? So you can't really tell me like on a molecule that which methyl is which, right? Flip it around or
Alright.
turn it around, yeah. I'm just thinking about that, because then like you said, then the other things ends up on a wedge. So it's kind of tricky to think about when you flip it like that. But I would say it would have, the main reason you wouldn't get the wedge here is because it would just be this diene that just comes in this state as opposed to that state, right? So if you drew the other one, it should still be correct, right? You just drew it the other way. I don't think it would be a wrong answer, right? Just got to make sure the other part is kind of like endo downwards, right? And the other two parts, right? As long as you point it out. I mean, the thing is, it was also drawn this way on the exam, right? So like, I would assume he probably did this too, but if you wanted to flip it for whatever reason, it wouldn't be wrong, right?
The other way to draw this without having the dashes for the second cyclic structure added would be just pointed downwards, physically drawn, right?
Well, I wouldn't do that because you're drawing a 2D structure here. So the only time you do the downwards lines is when you're drawing 3D structures. And the only time you do that is bicyclics and chair conformations, right? Because you're showing those in 3D, right? So everything else in bond line is 2D, right? So drawing a line without a wedge or dash is just drawing it in the plane, right? It's, even if you did like this, like I get what you're trying to do, but like, don't do that, because it's, he's not going to know whether you're trying to do that or not, because it's all 2D technically. But when you're doing things in 3D, right? Oh, whoops, that's right.
All right,
right,
thank you for clarifying.
Yeah, so in 2D, always show the wedges and dashes, right? In 3D, that's why you don't have to show it, because it's in 3D, right? There's no enantiomers there, Ali, because enantiomers really only form, right, for the most part in Diels alders, it's like when you have a trans dienophile, yeah, right? That's the only time you'll get. In this case, it's probably not an enantiomer, but actually, no, it would be, yeah. But yeah, only when you get trans dienophiles. Okay, so yeah, the question below this we're gonna skip. That's electrocyclic reaction, and then the next one is hydrohalogenation. This one's a bit tricky. You're gonna make sure you do it correctly, right? So this is where I was saying Markovnikov's rule, the way Klein teaches it, is not a good way of teaching it, right? Because here the whole issue we have is this is just a simple Markovnikov addition, right? So you guys saw this with like the, what is it? The butadienes and HBr, right? But the main thing you have to know is do not break aromaticity, right? So when this alkene eventually protonates, right? That, it's going to be resonating with the ring, right? But you never actually break aromaticity. Your final product, you still want it to have an aromatic ring, right? So despite it, having this conjugated system, right? You wouldn't move this position, right? So basically now there's two things you need to look at. This can basically protonate in two ways, right? We could get a carbocation that looks like, just change the arrows to, right? So we have a carbocation that looks like this. This is where someone was talking about resonance earlier. That comes into play here. Right, we have when it protonates, it could protonate this way and end up with H like that, or it could protonate the other way, right? This is why I said Markovnikov's rule with the whole thing with more H's doesn't always make sense, right? Here, both sides of the alkenes have H's, right? That's why whenever you think of Markovnikov addition, just think of it as forming the most stable carbocation, right? And this is that never fails you, right? Because now, if you have this, you can directly compare these two, 1 and 2, which one is more stable.
One,
Why is it 1?
because of resonance.
Right? So it's a secondary resonance stabilized with this aromatic ring, right? It could delocalize in the ring. So it's a very stabilized carbocation. Here, you have a secondary position, doesn't have any additional resonance structures, right? And this is why I hate that Klein talks about Markovnikov rule as the position with more H's gets the H. It's wrong, right? It's in a case like this, you can't use that rule anymore, right? They both had the same H's, right? So that's why whenever I teach Markovnikov's rule, I always say that you always form the most stable carbocation when you are, protonating your alkene, right? So in this case, we go through pathway 1, Cl, is it Cl? No, it's Br. I started looking at Cl. Br minus gonna come in and attach there, and you only get one product, should be this one. Br. Alrighty. And okay, so we are skipping. We already skipped electrocyclic. No, we could do number 5. Okay, so 5 is a mechanism question. These are always my favorite on exams, because I would do the rest of the exam really quick, and then I would just, if the mechanism was hard, I guess I would just spend the rest of my time on that. And this one's pretty easy though. So like I said, you'll always get these acid catalyzed mechanisms, right? So let's work through this. So, and you'll also always mention too, right? This is kind of why it's important to understand, always remember what a catalyst is, right? It's never going to be part of the reaction in the final product. It is something that helps the reaction proceed, right? It lowers the activation energy. But in terms of organic chemistry, some reagent that's going to come in, help your product, and eventually leave the same way it did. So if our acid is our, sorry.
I'm sorry, just like quick question, if you can answer in like one sentence. Carbocation gives you a positive, and acidity, acidity is like negative, right?
What do you mean?
Like, he had 2 questions. One of them was a format where he says, based on carbocation, I think rate them based on like strongest carbocation or something. Actually, never mind. I'll look at it again. He has answers for those.
I'm not sure about that, but generally under acid catalyzed conditions, you're forming positive charges. But anyways, let's start, right? So we're under acid catalyzed conditions. That means essentially you could consider this as just a source of H+. It's going to make your mechanisms easier. As far as I know, he allows it, right? Maybe if you want, you can draw H2so4, the entire structure. Actually, you guys should email him and ask if he's fine with accepting as a H+. I'm just so used to drawing it that I'm just going to stick to it. But in case he does,
I think he doesn't want to allow it because he wants to see
the entire electron flow. Okay.
Yeah.
All right. So I will go ahead and draw the rest of the structure. Okay. So, but essentially, right, when you have any sort of acid catalyst, the main thing is your proton, right? It's going to come in, it's going to help the reaction proceed a certain way, and it's going to eventually leave, right? And then it might do any other transformation. So the first thing you want to do is any mechanism is see what you had and what became of it, right? So if you notice, let's kind of highlight the structures here, right? Let's make that pink, right? So that's pink there, right? So over here, the pink part is still present, right? It's here. Oh, wow, that actually worked out perfectly, damn. So we have some sort of similar things here. Now let's see what's kind of changed. We had this ketone group, and now we have, what's it called? A methyl group and an alkene, right? If we kind of tried to label and keep track of our carbons here, we could say this was 1, 2, 3, 4, right? This is 1, 2. Did I draw an extra carbon here? No, I didn't. Sorry, I just labeled them wrong. Oops. One, 2, 3, right? So we have 1, 2, right? And this carbon is still the pink one, so that means this methyl group had to be the third carbon, right? So essentially what happened here was we somehow lost our carbonyl group, right? And this methyl group is essentially sticking up. But what we could really see, right, is this carbon formed a bond with 2, right? That bond right there, right? And that kind of gives you the first insight into where the mechanism is probably going to start, is that you need to make this electrophilic, right? And it is to a degree electrophilic, but remember, this is why I said under acidic media, what was like one of the first things I taught y'all? What kind of charges do you expect in acidic media? Neutral and positive, right? So if we directly had this nucleophile attack here, what's the issue with this mechanism now? What do we get?
So over there's resistance though, because well, there should be resistance, right? Because O is already like bonded well.
Well, yeah. Well, that's okay. That's actually a good point to bring up, right? So O is in a double bond, right? But we essentially want to make this very electrophilic, and we can do that, right? Because we are an acid catalyzed media, and what's the most electron-rich thing in this entire first molecule?
The O.
The O, right? So the first step here is
So
going to be the
H.
Sorry, what was it?
No, it's what you said. It protonates.
Yeah, so it protonates. Okay, so let me just continue with that. Right, so we're going to protonate first. Let's start moving down. Now we're going to zoom out a little so we can draw everything here. Now we have a protonated carbonyl, right? This is now extremely electrophilic, right? Because this oxygen wants to go back to being neutral, right? So now, remember, we are forming a bond from essentially this carbon to that. So what we could do, right, is we could take, what's it called, carbon 2 here, right? Or the pi bond between 2 and the bridge, right? And that remember, pi bonds can act as nucleophiles. So we're going to break aromaticity for a second. Let's make sure I draw it right, right? And we're forming that bond to 2 now, right? So once again, if we keep track of carbons, right, we are forming a bond from, let's call this A to 2, right, as we had. So this was A here, right? And now we can do that. The electrons push up, right? This is why this still comes in from basically Orgo 1 stuff, because the second part of this mechanism, when we get to it, is something you learned in Orgo 1. Whoops, that aromatic bond is gone, right? So we get 1, 2. So once again, if I keep track of carbons, keep labeling that as 1, 1, 2, and 3, right? And this is A here, right? A bonded to 2, this is 1. This is 3. At 1, there. No, sorry. At 2, there should be OH. There we go. 2's OH, 1's there. Okay, see, that's why it's always good keeping track of carbons, right? So now we have this intermediate, right? Are we missing anything here?
Yeah, positive charge.
Where?
You have a positive charge on the OH and a positive charge on the carbon that lost the bond.
Yep. So
one-
there's not a positive charge on the carbon on the oxygen though, but that's the only positive charge we're missing.
Oh yeah,
right?
because okay, never mind.
It gain backs. Oh, no
Yeah.
worries, right? Just don't do that on your exam though.
Yeah, I forgot.
Yeah. Yeah, that would be kind of a steric. It doesn't really matter. I'm just looking at it now and it's whatever. The mechanism doesn't, you can't prove which carbon turned into what. Anyways, now we have to regain aromaticity, right? So luckily for us, we have conjugate bases present, right? I'm just gonna use water because technically water is probably present too. I guess you could use the conjugate base here, right? I'm just so used to using H plus in water, right? Because like H2so4 will not exist in a non-aqueous solution. It's always going to be aqueous. But if you want to, you could probably use HSO3 minus. Doesn't matter.
I'm also confused because in the textbook, they use just H plus in water, even though you have SO4.
Yeah, because you know what? For consistency's sake, I will go ahead and use that. Because I did that in the first step, and this might confuse some people, right? I always use H3O plus or H plus water, right? Because remember, any acid and base, a strong acid in water, right, completely dissociates. Oops, I drew that wrong. Professor used H3O plus. So like I said, you're always going to have, you know, hydronium plus your conjugate base, right? So your water and hydronium are always present, right? That's why I always use either H plus or H3O plus in water, right? I guess for the sake of keeping it consistent, right? Because you guys said he used the H2so4 fully, I will go ahead and do that too, right? So now this, right? We said it's going to regenerate our catalyst here, which is what this step is, right? Boom, right? And we're regaining aromaticity, boom, right? So now we're almost to the finish line. People are typing a lot right now. Give me a second.
Can we just take a hydrogen from carbon 1 and put it on the carbocation? And then we can just put the pi bond between 1 and 2.
If you did that, right? So if you take this, right? First of all, that's too far for it to do that, right? It has to be next to it. Second, if you created a pi bond after that was left, what's the issue here with this pi bond?
Oh yeah, I see. It's like 5 of them there.
Yep. All right. So as much as you want to skip steps, right? Don't do it on your exam. Okay, so now we're on the second part. And we're almost close to the product, right? Now, does anyone remember basically, where the hell is our product, yo? Oh, it's right there. That pink one there, the one I circled, right? Let's remove that circle. Going from an alcohol to an alkene. Does anyone remember that reaction from Orgo 1? Nope. That's an addition reaction. If you're forming an alkene, what kind of reactions are those? Elimination, but this one's not an elimination. It's not E2, it's E1, right? So this is acid catalyzed dehydration, right? And a lot, like I said, like a lot of these mechanism questions, like, yeah, your kind of substrates get more advanced, but they will do some sort of, like, if you have alcohol in it, you're going to go through an acid catalyzed dehydration, right? That's why whenever I teach that mechanism, I always say to remember it, because like you said, one semester later, here you see it again, it's still part of a mechanism, right? And so this next step is essentially going to be at E1, right? So yeah, we're under acidic conditions, as Mohammed said. OH is going to gain a hydrogen. It's going to leave. You're going to form a tertiary carbocation, right? Conjugate base is going to come in. It's going to deprotonate. That's how you're going to get your alkene, right? That's why if you remembered, those certain acid, that's why if you remember all really the acid catalyzed stuff, a lot of them repeat themselves. There's certain steps like you need to figure out how to do, but after that, you'll see it's very similar. It's just a series of deprotonations and removals, right? And these next 3 steps, I literally just said them, right? So you don't even have to, you could work them out without even remembering. I don't even know what I'm rambling right now, but like I said, stuff will always come back, right? So it's good to remember, I guess. Now a hydronium ion, right? Gonna kick out. The main thing though here is, right, it's E1. What does the 1 mean in like SN1 or E1?
Rearrangement.
Well, not exactly. It's first order, right? Right. E1 means it's elimination first order, right? First order means it depends on only the substrate. And also it gives you insight to the mechanism that it's not going to be concerted. So when you reach this point of OH2, do not do this all in one concerted step where your H2so4 minus comes in, grabs the proton, kicks this off at the same time. The first step that will happen is the leaving group leaves, forms your carbocation, right? And oh, I missed some bonds here. And then, you get your final product. So in an E1 reaction, right, never skip the steps. Same with SN1, right? Your carbocation always has to form, right? So don't try to like quickly do this here with the protonation and, alkene forming, right? You got to show the carbocation. Okay, we're almost there. Plus, right? Can this rearrange? Or I should say, will it rearrange?
Yeah, would the hydrogen and carbon 1 come down to make a double bond?
If we did that, right? Well, rearrangement, right? Just to, I think you're on the right track. That's going to be forming the double bond, right? Rearrangement, I meant is the carbocation going to rearrange to another position, right? No, right? Because this is a tertiary benzylic position, right? If it goes to the secondary position or the primary position, it'll become less stable. So we're lucky, right? That's what I'm saying. If you ever notice, like, let's say if this was a little bit more difficult and then you ended up getting here and then you had to create an alkene somewhere else, look for rearrangements, right? So whenever you get to a carbocation, just check for rearrangements. In this case, the mechanism is asking you for that alkene, so you don't have to rearrange it. But in case it ended up somewhere else and you're confused, how the hell did it get there? Think of what could happen with carbocations, rearrangements, right? So you're at the step, no rearrangement, right? Now you could just do your final part, which is we're going to use H2so4 minus again. And and we get our product. It's all about really with these acid catalyzed mechanisms, which is a good chance is probably what you're going to get, right? Just understanding what is going to get protonated first, and then it's literally just electrons flowing from place to place, right? The first thing that happened was the most electronegative thing, or the most thing that's likely to get protonated was that carbonyl up there, right? And then after that, you just, pi bonds can act as nucleophile. You have a very, electrophilic group. That's a bond you're trying to create. So that's why I say map out the structures, list out your carbons, see what new bonds you create. You could always figure out a mechanism, right? That's why I always found them fun, because it's like the other questions, it was just, remembering what reagents does. This was always something new, right? But to each their own, right? Okay, and I guess plus water, right? It's gonna be chilling there. Yep, so that's the mechanism.
Are we
not
gonna
too
have the
bad.
whole class for the exam?
What?
Are we gonna have the whole class for the exam, like the class time?
Yeah, I think so. I mean, he didn't say otherwise, so I'd expect you get the full hour and 50 minutes.
All right, cool.
Okay, so now we just have 6 and 7 left. Oh no, not 7. Yeah, 6 and 8. Okay, and then we're done. Okay, let's do mini here. Okay, so 6. Okay, using molecular orbitals, right? Display, oops. Right, if the following cycloaddition is thermally, I don't know why I'm not copying and pasting this instead. That way I don't have to read this. Shoot. Okay. Okay, let's see the question there. Let's take a few seconds to read it. Right, so this is the same MO theory stuff, right? You just got to be careful of what your dienophile and diene is. Dienophile, you could probably, well, we'll see, right? So here we have just one single bond, right? And here we do have one single bond too, right? But I don't want to call these the diene and dienophile. If we just looked at these to do a cycloaddition, right? Which one is electron poor and which one's electron rich? Or I should really say which one's electron rich.
The one with the negative charge.
Right? And the one with the negative charge. So in this case, we have an allylic carbon ion, right? This has a lot of electron density. Essentially, it has 4 electrons delocalized over 3 carbons. Here you have 2 electrons delocalized over 2 carbons, right? So this is the molecule that you'll use the what? HOMO or LUMO for?
HOMO.
HOMO, right? And here we use the LUMO. So let's draw those out.
I remember the professor saying you can use either, like just as long as they're the opposites.
I mean, I'll try that out later to see if it works. But generally, what I always do is the electron-rich species donates its HOMO. The electron-poor species, or at least electron-poor in comparison, donates its LUMO. That's how I do it. Because Professor Andy asked a question with this. Well, he did it similar to this. It's what's called an inverse demand Diels Alder. He did it on one of his exams. And it was really the dienophile was electron rich and the diene was electron poor. The same concept that's applied, that the HOMO always comes from the electron rich species. LUMO comes from electron poor. But I mean, I can work it out later and I'll ask your professor tomorrow or something. Okay, so let's draw out. So here we have How many p orbitals here?
3.
Three. Right. So we get how many molecular orbitals?
3.
3. Right. So the first one is easiest. This is the only one. Maybe you've seen this in class. So the thing is with the so the first one, we're all good that they're all in the same phase, right? The second one, right, is how do you get, the node? So that thing is the node is what is it? Kind of node. Node is through the orbital, right? It's like the best way I would describe it, at least. I forget if it's a planar. It's a planar or linear node. I'd have to look that up, right? But that way you basically notate it if the node is going through an expected orbital, you could just put a dot sign there, or you could draw the orbital and just like cross it out or something. But I was always taught to just draw a dot when it was like I forgot if it's called an orbital node or a planar node. I forget the terminology, but essentially, you guys hopefully understand what I'm trying to talk about here is that the node is going through that orbital, right? So that entire orbital there is going to have no electron density, right? That's what a node is, right? And if you look in terms of the wave, it still makes sense, right? It's still symmetrical, right? And we have one node through these two orbitals. So that's for the 3 pi electron systems. That's how you draw the molecular orbitals if you ever got those. The same would happen in a carbocation if you did this, right? The only difference here would be that this would only have 2 electrons, but this would still have a 3 orbital system, and the molecular orbital diagram would look the same, right? And the last shell should just look like opposites, right? And we have 2 nodes between these orbitals. And if we see this, right, that's our 2 node system there, right? So the wave thing still works, right? That always works. You just have to remember that in this case, the node is through an orbital, right? How many electrons did we have? 4, right? And this is the HOMO, and this is our LUMO. And now if you look at the other one, how many p orbitals? Oh, sorry, somebody. Thank you for answering that, Christopher. But yeah, what he said is, how do you know it's 3? It's because based off the molecular orbitals are based off how many p orbitals are conjugated with each other, right? So remember that this is a carbanion, right? It's part of a p orbital. Oops. Right. So here we have 2, right? So this one is simple. Oops, let's draw it this way. In phase, 1 wave, out of phase. Only 2 electrons. This is our HOMO. This is our LUMO, right? Now we're kind of doing the same two things, right? We're seeing if the HOMO and LUMO can interact with each other, right? So we could draw this carbanion. Oh, good thing. Reminder, otherwise this would have shut off. Second, let me put my surface on charge here. Okay, so we take the HOMO here, right? So we could draw it like this, there, right? There's the lone pair here, right? That's where our negative charge is, and this is our other orbital. Those are different phases from each other, right? Should put the electrons in there. I guess I'll put them in there. Why not? So now the other one, right? If you want to draw it overlaid, same thing, right? We have this and this, right? remember, right? Always do a flip check just to make sure it lines up, right? If we flip these, if we flip this way, right? Then it looks like, oh, why is this lagging, yo? This wasn't making contact, sorry. That's 6-membered. Yeah, it's 6-membered enough. Okay, so if we flip them, right, we are flipping this entire molecule, right? So that means this side is now here, right? So this is now the, oh, whoops, I just drew it the same way. This is here. I don't know why this is, I don't know, whenever I put this thing on charge, it's always super laggy. It's funny because you'd expect the opposite, right? And this should be flipped, right? So literally, if you just turn the molecule on its side, right? Do not mess up the orbital system. That's the thing. Remember, we did this when we did this problem for the first time, this kind of problem, right? Just, changing the face, right? Hopefully everyone's clear on that, right? So if this was carbon 1, 2, 3, 4, 5, and 6, right? Flipping it, this is now carbon 1, 2, 3, 4, 5, 6, right? Just make sure you're doing the flip right. Oh, sorry, I flipped it. I did it the other way. Oops. There you go. But if you label the carbons, you won't mess it up, right? Think of it as kind of a mirror, right? So now we see the interactions.
So it's photochemically allowed, not thermal.
No, so we didn't excite the electrons. We just changed the face of the molecule. It's a good point you brought up. We did not change the LUMO or anything here, right? All we did was change the face, right? So I did no chemical changes here, no electron changes. If you look at the first molecule I drew here, right? It says 1, 2, 3, 4, 5, 6 like this. I flipped it over. So now 1 is at this position. That would mean 2 is here, 3, 4, 5, 6, and the orbitals are still the same, right?
What was the purpose for flipping it? I'm sorry.
Just to check to make sure if if I drew it the other way, it would line up, but like some people, the main reason I'm showing this is like, I could have just do it correctly to begin with, right? Like this and this, that's it. Oops. Right? But if you drew it like, picking these orbitals like this, like you might have drawn it the other way, right? So you could always do a complete flip of the molecule as long as you're not breaking any bonds or changing the orbitals, right? You're literally just changing the face that is approaching the other LUMO, right? Like the bottom side is now the top side, right? So that the flipped is just to make sure that the orbitals line up, and they do, right? If after a flip or not, and you still don't get no lineup, right, then it's not going to be thermally allowed, right? So here, since these both line up, right, this is check, this is thermally allowed, right? So just to be clear again, right, I could have just drawn it correctly to begin with, right? But if I was to, if you drew it like the other way and you thought it would be wrong, just always do a flip just to make sure, right? Right here, all I did was I flipped it over. Like if you grab, I don't know, everybody, grab your phone, right? And the corner close to you, right? Right. If you flip it, it's going to be away from you, but the orbitals, right? Their phase sign or whatever, right? There's just going to be on the other side. So you're just making sure it can line up. Like if you're putting it underneath this way, or you're putting your phone like top up, right? Or bottom or top down, right? But you're not, what's it called? You're not actually changing it. You're literally just rotating it, right? It's a lot easier to show in person, but Hopefully understands the rotation or flip I just did. I did not do any chemical changes. I did not change the orbitals. I literally just changed the face that's approaching the HOMO of the other molecule, right? So I always do the flip just to make sure, like if I didn't get it the first time, maybe it works on the other side, right? And if it does, boom, it's thermally allowed, right?
Now, what if you use the HOMO of the other molecule and the LUMO of the other molecule? But just switch them over.
Yeah, then I mean, looking right at it, right? You have two same phase. Basically, you have two things on the same phase on each side here, right? And if you just did a flip on the other one, right, it should still work out, right? So yeah, in that case, just quickly looking at it, you could see that this, like, if you had this as the bottom, right? This, and then you had the other one, right? It would be, what is it? This, oops. And then we had this, right? But now we just flip it, right? Then it's all, right? That's just flipped. And it lines up still too. But the reason I chose the other one is because it's more electron rich, right? I don't think, let me actually see, since I have the answer. I would expect he did it the same way.
Because I'm still confused because I thought it was, if it's flipped, then it means that it wasn't thermally allowed. Rather, it was photochemically allowed.
So the thing, right? I think what you're is like when we're flipping it, right? We're not doing any chemical changes. We're not exciting it. We're not changing those orbitals, right? If I were to draw these orbitals, right? Using the phase notation, like
It's like a conformational change rather than a.
It's not even I guess conformational. It's really just the face you're approaching it with, right? If you consider this side of the molecule, the top face, right? This other side would be the bottom face. Like look at these two bottom orbitals, right? This is uncolored and colored. At carbon 1, it's colored. At carbon 1, it's uncolored, and carbon 2, it's colored, right? So if I literally flipped it over, so I'm showing that face up, right? At that position, it's going to be up, it's going to be down, right? So the photochemical change is that when you actually excite it with light, it's going to move the electron to the next orbital level, and that changes everything, right? That changes which orbital you're using. I'm not actually changing the molecular orbital here. I'm using the same one. I'm literally just making sure it can, line up properly, right?
But just to reiterate, when it's not thermally allowed, it's photochemically allowed. That's just a given rule, right?
I think usually, yeah. As far as I know, for the most part, once you excite one thing, it should line up. I don't want to definitively say that, but generally, usually he'll only ask you if it's thermally allowed, or if he asks you why it's photochemically allowed, there'll be enough proof to show why, right? But I don't want to say one or the other because there might be exceptions to that, right? That I don't know about, right? But in this case,
I apologize for extending the time because it's like already 12, so I don't want to.
Yeah, no worries. We have one question left. Let's just finish that up. It's a simple synthesis question and we're done. Okay, so that's 8. And yeah. Okay, simple enough. I think we might have done this. I think we actually did this. Did we do this? Otherwise, yeah, I straight up think we did this. We did this yesterday, right? Almost positive we did this yesterday.
Yeah, I think we did it.
Was this confirmed? Whoa. It doesn't seem that way too much there. Okay. Yeah, okay. We did do it yesterday, right? Why did I have it written like this? Oh, let's erase that for the final product. Oh, I was just checking. Okay, yeah. So okay, so yeah. We'll actually end there. So that's the solution for that problem, and you could review the end of yesterday's recitation. Okay.
Still got brain cells, bro?
Yeah, I'm fine, man. Yeah. Anyways, hopefully that covered more or less everything. Well, I tell them as best as you guys can do.
During the exam, you could just like give us little like hints and stuff in there, you know, since we're like, you know,
Yeah.
walk over and like point at something, you know.
Yeah, maybe. Okay, everyone, have a good night. Get some sleep, and yeah,
You too. Thank you.
best of luck on the exam. I'll see y'all Tuesday.
Said we did 8, right?
Sorry, what was that?
We already 8.
Who, me?
Yeah, we did it before.
Oh, we did. I thought you said, did you already eat? I was just like, yeah, man, I already ate. Yeah, we did 8. This is what I was showing. It was 8. Yeah.
All right.
Yeah. All right. Have a good night, everyone.
Oh, by the way,
Yeah.
if people
You can
want to
go.
know this, but one person asked if he expects us to know how to use blocking groups, and he
Mhm.
said yeah, because he went over desulfonation.
So yeah, that's what I was showing you in one of the examples yesterday. So
It's literally sulfonate to hold like 2.5
yeah, this
electrons.
I think we did it in this one here, right? Sulfonation.
Yeah, it's not bad. It's literally just sulfonate when needed.
Exactly. Basically, when you want to block a para position or basically block a certain position, right? You could just sulfonate and then do your next reaction, desulfonate, right?
All right, thank you.
Yep.
Sure, can I just have one last question and then that's it?
Yep, go for it. Someone else had a question too.
Yeah,
Miss
with
Shizda, if you're still there, I'll answer though. You asked me at the
Yes, I'm
beginning.
still here.
Okay.
with question 6, the orbital one, could you say you just flip the ring just to check to see if they would match up regardless, or yeah. So I was wondering, like, did you just ring flip it to check to see if they would still like match up, or I don't think I can hear you.
My mic's been off. So the main reason I did it this way, right? Because when I drew the orbitals, right, I drew them. This one, the one on the left is shaded. The one on the other one is shaded on the bottom, right? And I just, I would expect a lot of people to draw it that way when they're trying to line it up, right? And then they might see, yo, that's not thermally allowed or whatever, right? That's why I always say do a complete molecular flip just to see if it lines up, right? Because just because of the way you drew the orbitals doesn't mean, they're in space. Remember, in space, they'll always interact in a way they can interact, right? And like, in this case, they'll make sure they can line up because, in 3D space, you could like move around, right? But on paper, right, you might draw it just like I drew it here and think okay, no, this isn't thermally allowed. I don't know what's going on, right? But the question specifically said it, well, determine if it is thermally allowed. That's why I always do a full flip just to make sure off the other face if it does it line up, right? But we did not do any chemical change. We did not excite it or anything. We're literally just changing the face of approach just to make sure, like complete, like, because there's only 2 faces, right? So if we just make sure on both sides it doesn't line up, right, then it won't be thermally allowed, right?
I just wanted to make sure because like I was confused if you did it for like a specific reason or you're like, no, I just checked just to check to make sure that
Yeah,
all dimensions
in that
within
case,
the
like I could have just drawn it correctly to begin with, but I did it
Mhm.
just to show that in case people drew it that way and messed up, like they wouldn't like you do that check, right? Just to make
Yeah.
sure if you have it initially, but don't
Yeah,
mess
'cause-
up your orbitals, right? That's the main thing. Make sure you flip it properly.
Okay, just making sure because that's how I drew it too, so that's why I was a bit confused. But thank you.
Yep, no problem. Chris, OneDrive, it was empty. Give me a second. Let me find the other link that I had for it. That's weird. Okay, actually, let me stop the recording now.